breaking all the rules. From Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down. Actual education making scholars all around. Perpendicular minds, angles sharp as ice. Maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex. Quantum theories on deck, breaking all the specs. Relativity theories, worlds getting small. Grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep. Graphing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold. Brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down. Actual education making scholars all around. Perpendicular minds, angles sharp as ice. Maths and physics, yeah, the future's real nice.
All right, what's up, everybody? Yeah, we are getting fives. Yeah, positive thoughts, guys. All good, all good. All right. Welcome, everyone. Hope you guys can hear me. Yeah, great, cool. I'm gonna give people like maybe 5-10 minutes to mosey on in, but good job to y'all for being on time. Let's go. Great, yeah. AP Physics was moved up this year. It's usually like the 16th. So they moved it up like a whole week. It's kind of annoying. But that's why we're here. Your exam's tomorrow. You all are all going to do fantastic. Amazingly. I would also like to reiterate that the exam is very much curved. So don't feel like you have to get, you know, a 90 or 80 like you're used to having to get in your regular school classes. I think the cutoff for a 5 is like a 60 or something. It's so low. We can actually look it up. Here's AP Physics 1. They have the score distributions. I'm always curious about this. Let me see. It's practice exam. There we go. Scoring guidelines. There we go. Scoring statistics. This is always interesting. Let's see the distribution. It's a 70 to 75. Yeah, maybe it's a 60 just to get a 3. There we go. Okay, cool. Yeah, so this was the distribution of... It's been going up too. AP Physics is traditionally one of the worst scoring exams in the AP like coursework, which is... yeah, troubling, but I understand why it is. It's because most people who are already naturally inclined to wanting to do physics and go for AP Physics C. AP Physics 1 is for people who are like, we're trying to get you guys into physics. You may not necessarily be 100% gung-ho into doing it, but trust me, it's a great thing to get credit for, especially going into college. It's one of the harder classes you have to take in college as well. It's 65 to get a 4? Okay. This was the distribution on the individual questions. So yeah, little preface to how this is going to work. So I'm going to go through the I'm going to go through the actual exam that was given to last year's students, and we're going to go through the FRQ section, which I think is usually the hardest part of the exam. And once we're done with that, I will then open up the floor to if any of you guys have any generic questions or you have any specific practice ones you were working on that didn't make sense. We'll show you. We have a whole like website system that we use for submitting screenshots. The website for that is actualofficehours.com. I'll dump this link. I'll pin it here later for you guys. But what we usually do this is a nonprofit called Actual Education, and we stream 3 to 4 times a week, and we help out students, high school students, college students, middle school, whatever, in any sort of math or science questions you guys need help with. And so usually how the stream works is we'll just be on here on YouTube, Twitch, TikTok, and students will come through, and then they'll just put their username in, and they'll drop a screenshot in, and just hit upload. And then that'll get put into a nice little queue that we have, and then we end up selecting questions throughout the stream to help you guys out. It's like free tutoring fun stuff. So that's the generic stream of how this works, but for today's stream we're doing a special edition to help you guys out, specifically with AP Physics 1. So I'm telling all my usual viewers that, like, you know, pause, because we're not doing that today. We're not doing the usual stream. We're doing AP Physics 1 only today. But if you ever need help with any of your other classes, whether that be chemistry, biology, stats, calc, whatever, please feel free to come on by to check out our other streams throughout the year. Again, 4 times a week, sometimes 5. If you click here on the streaming schedule, this is a cool little calendar that shows all the people, not just myself, that stream free math and science help on. This is primarily on Twitch. We're on all the platforms at once, so. But you can always check this out. I'll post a link for it later. Nikki says two AP exams in a row tomorrow. This will be so rough. AP Lit, then AP Physics? Oh, no. Oh, that sucks, man. Is AP Lit the one where you have to write a bunch? I mean, I remember there's, like, language, and then there's Lit. There's 2 of them. One of them you have to write a bunch of essays, which is really painful. And then, yeah, Nightbot will come in the chat and say things, but don't worry about him. How's the score for a certain grade determined? If you look up AP Physics score calculator, it says 54 out of 100 is the predicted. So it changes. There is no hard line on what the score is to get a 3, 4, or 5. They do it based on, like, percentages, and this is kind of more of a statistics thing. They'll do it based on, like, percentiles and whatever. So those online calculators are approximates and are estimates, and they're usually pretty good, but it can shift. So don't take it as like a hard limit on them. Oh, language is that? Yeah, okay. Language is when you got to write a bunch. Yeah, I saw in my own Discord a lot of people were complaining about AP Chem today. They said it was an absolute nightmare. They're just like, it's terrible. No. I'm sorry. I teach a lot of chemistry too, so if you guys ever need help with chemistry, I can help you guys with that. Help you guys out with that as well. But okay. 4 more minutes, and then we'll go into it. I see people coming in, rolling in. Oh, and that timer. Let me fix that timer. Usually that timer is... Yeah, we're going to go for more than 2 hours today, probably. For sure. The FRQs were rough. What form did you have? Some people told me that, like, Form J was apparently especially nightmarish. There we go. Bump the time up. Yes, volume flow rate. We can definitely do that. Yeah. It's interesting. So they added fluids last year onto the AP Physics 1 exam. It used to be a part of AP Physics 2. And last year they decided to shuffle some things up and they added fluids. On last year's exam, in the FRQ section, as you'll see we get to, they didn't do anything super tough on fluids. I think they just did buoyancy, which is kind of a pretty simple topic to go over. But yeah, after we go through the FRQ practice, what I'll open the floor for is you guys to submit screenshots of different things you want to go over. That can be like practice questions you have, or maybe generic topics, and we can find different ones to go through. So yeah, you had J and it was hell. Uh-oh, dude.
Oh no.
I'm sorry. Yes. Yeah, and Nightbot should tell you where that's where the screenshots, if you guys want to throw in questions you want to do after. We'll probably spend like an hour and a half doing the FRQ. And then I'll stay online as long as I can to help you guys out with any other user questions. But okay, I think we've been waiting around a little bit enough. So let's start off the stream and see what we got. All right, cool. Here we go. So I have here the AP Physics 1 FRQ from 2025. So this is the official exam that got published last year. Again, you get an hour and 40 minutes for it. This, I think, has 4 questions. Some of them are pretty involved in terms of like multi-part questions. So Some you have to work on a little bit more time or less time. But okay, let's start here. Did they not give you an equation sheet to start off with this? I thought they did. Okay, well they don't. Okay. I'm pretty sure you guys get an equation sheet maybe on the beginning form for things. But there's not too many equations you have to memorize for this, so I will go through this. Feel free in chat if anything doesn't make sense or you're like, wait, hold up. Just type it. Just be like, hey, can you explain that step again? Or why is it like this? Or that doesn't make any sense. And I'm happy to, I'll hold up and we'll go through the questions you guys have. All right, so let's see. Version J. This is the nightmare version for chemistry. Okay. Let's see. A student has a cart of mass MC and a block of mass 1/5 MC, as shown in Figure 1 here. At time t equals 0, the cart is moving to the right across a horizontal surface with constant speed VC, and the student releases the block from rest. At time t equals t1, this block falls down and collides and sticks onto the top of the cart. And then the block does not slide, is what we say. And then at time t equals t2, the block cart system continues to move to the right with a constant speed of VF. So, yeah, maybe important. Let's put let's say VF here. It'll help us out. I always like to write down the stuff from the word problem on here. It's easier to look at it than this is all great. Cool. And then we know this is traveling at velocity VC. All right, let's see. On the axes shown in the figure 2, sketch a graph of the magnitude of px, so that's momentum in the x direction, of the block cart system as a function of time t from times t equals 0 to t is greater than t2. Great. Okay, so let's see what's happening. So momentum, as we remember, is going to be equal to m times v. And a lot of times we want to talk about the total momentum. That is going to be the sum of mv. So you're going to add up all the masses and the velocities of those masses. And this also needs to be done in terms of components. So you need to only look at momentum in the x direction and only look at momentum in the y direction. So for this question, all we care about is stuff in the x direction. So I'm just going to call this p total x. And so that's going to be the sum of the masses times their velocities in the x direction. Now, looking between t equals 0 and t equals t1, we have the cart here, MC, which is moving at a velocity VC. Okay, so I can say, okay, cool. So at t equals 0, we have MC VC. And then the momentum of the block here is going to be 0. Because this thing is not moving at all in the x direction. It has no velocity in the x direction. So that's it. That's just set. Then at t equals t1, this block is going to fall down and stick with the cart. So let's see, t equals t1. And so we're going to have a couple things now with momentum. So the cart will now have a velocity, which we're going to assume is VF. So that's the final velocity. The velocity is not going to change in between when it's stuck here and when it just keeps moving. And then also we're going to have this block now has momentum in the x direction because it is moving with the cart. And so that is going to be 1/5 MC VF. Okay, cool. Now here's the key thing. We want to graph the total momentum of the whole system. And there's not as much math in this part as more of conceptual things you need to know. And that is that total momentum, so we can say total momentum of a system is conserved if there are no external forces. So, between the cart moving without the block attached to it and then the cart moving with the block attached to it, technically in the x direction, there was no external forces that acted on either of these things. We just dropped the block. The momentum in the y direction is not conserved because there is an external force, and that force is gravity that's pulling the block down. But this question is specifically just asking about momentum in the x direction. And so because there's no forces acting externally on this whole system in the x direction, you can just draw a straight line all the way across. And so this tells you that there's a constant total momentum. And let's see, do they want anything else? They want an explanation at all? No, they just wanted it. Okay, so just draw the line. Okay, cool. So all you have to do is draw that the momentum is not changing between t equals 0, t equals t1, and t equals t2, because there are no external forces acting on the system in between any of those time points. Okay, let's look here at part 2. Now they're saying derive an expression for the final speed of the block cart system after t equals t2 in terms of all these MC, VC, and physical constants. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. Right. So, I mean, we kind of already wrote the statement here, which was this. So maybe we would actually probably want to, let's put this over on this part. Just for when they're grading, you kind of want to keep things in the correct section. So this is the statement, which is that momentum in the x direction will be conserved because there's no external forces in the x direction. And then if we want to figure out VF, well, we can look at this. Let's pull this over. Which was figuring out what the total momentum was at the different time points. So at t equals t0, the only momentum we had was from the cart that was moving at a velocity of vc. And then after a long amount of time, so we could say, let's say t is greater than t2. Now you have momentum from the block that is attached as well as the cart that's still moving. So the total momentum here has to equal the total momentum here, which we've represented as these equations. And I'm just going to set them equal to each other like this. So I'm going to say mcvc is equal to mcvf plus 1/5 mcvf. And then the nice thing here is that all the MCs are going to go cancel. So we don't even care about these. Cancel, cancel, cancel. And then what we're left with is VC is equal to VF plus 1/5 VF. So that's going to be 6/5 VF. And so rearranging for the final velocity, you're going to get that VF is equal to 5/6 VC. And that makes sense. We would imagine the total velocity here to be less than the total velocity here, because you have more mass that's moving in this case. If the cart was accelerating or deaccelerating, would it be nonlinear? True. Well, so if the cart is accelerating, then from F equals ma, right? Any amount of acceleration, Jonah, means that you need to also have an external force on it, and then momentum's broken. Right? Conservation of momentum does not work if you have external forces acting on it. These types of questions, you can have kinetic energy not being conserved, because you can have energy being lost to like deformations, you can have energy being lost to like friction and heat, but the momentum, total momentum does not change. It's actually kind of cool. Do you remember, right, that P is equal to mv? Here's kind of a fun little trick here. What happens if I look at the change in momentum, let's say, over the change in time? And so I look at, oh, okay, well, the change in momentum divided by the change in time would also be equal to the change in the mass times velocity. Let's assume the mass is not changing for something. So you would just get this. This is a little bit of calculus, like not too scary. We're going to do, it's really basic. And so what you get here is that, oh, change in momentum over change in time is equal to m change in velocity over change in time. But we know that change in velocity over change in time is equal to acceleration. That's from like kinematics, right? Change in velocity over change in time is acceleration. So this is also equal to force. And so this is kind of cool. This shows you that, oh, well, if the rate at which momentum is changing has to be equal to a force. So if there is a force, momentum is changing. This also is where impact comes from, or impulse, sorry. So from this, you guys probably also remember that like delta P is equal to F delta T. And then delta P is the same thing as M delta V. And so this equation right here, this is impulse. This tells you the mass times the change in velocity is also equal to the force being applied times the duration, the delta T at which that force is being applied. Yeah. This is what I love about physics is because everything just is self-consistent. Everything connects to itself. You learn very, very early on in physics F equals ma, and then you learn that P equals mv. But then using math and things like derivatives or like change in things or change in time, you can eventually rederive or come up with these other equations that you end up memorizing and learning later. They all come from the same thing. It's pretty cool. But yeah, that's a good question. So if there's any acceleration, then you have external forces, and then delta P is like no longer zero. So momentum is changing, and you can't do conservation of momentum. All right. So that was us solving for the final velocity. Okay. And then it says, derive an expression for the change in kinetic energy. Ooh, okay, cool. This is a cool one. So here, let's label this as like question 2. Question 2. Let's look at question 3. So now that, yeah, the change in kinetic energy. Great. So, let me just copy these. Work smarter, not harder. Otherwise, I'd have to redraw all this. Oh, no. Yeah, let's get rid of that. There we go. There we go. That was our first situation. Now let's pull this one in. Cool. All right, so let's figure out what the kinetic energy is for these two situations. So we remember that Ke is equal to 1/2 mv squared, which in the beginning situation, block has no velocity. Cart is the only thing that's moving, and it was moving at Vc. So we could say the kinetic energy for situation 1 here is just going to be 1/2 mc times Vc squared. That's the total kinetic energy for the beginning. Let me move this over a little bit. Okay, in this case, now these two things are moving together, right? So this is now going to be an m total, which is equal to 6/5 mc, right? Because this was 1/5 and this is a 5/5. So now you have that kinetic energy is going to be 1/2 6/5 mc. And then what's the new velocity? Well, the new velocity is this. So 5/6 Vc squared. And what do they want? They want derive an expression for the change. Okay, so I usually when they want the change of something, so the change, which is equal to delta, that's in this case delta Ke, that's going to equal the final minus the initial. So we're going to just do this minus this. So let's grab that. So we're going to have that one squared minus 1/2 mc Vc squared. This is where you got to do a little bit of algebra. I'm going to factor out a 1/2 from both of these because it's right there. And then let's see. One of these 5/6 will cancel out with one of these 5/6, with one of these 6/5, sorry. And then there's another 5/6 because this is squared. So this is going to be mc Vc squared. So mc Vc squared. And then one of these cancels out with one of these. So you're just going to have 5/6 left there. And then that's going to be minus mc Vc squared. So this is the same thing as minus 6/6. So 5/6 minus 6/6 is -1/6. And so we have 1 over 12, 1 over 1, it'll become 1/12. Negative 1 over 6 MC VC squared, or negative 1/12 MC VC squared. So there you go. This would be the final part for 3, and that would be the change in kinetic energy. So even though momentum is conserved, you're still losing kinetic energy. And you can think of that loss in kinetic energy of, well, as the block falls down and just instantly sticks to the cart, there must have been some deformation, or as we're going to see in the next part, there has to be like some friction that keeps those two things together. What's up, Bella? I'm not streaming this on Discord yet, just because I'm just running through this without any commentary, but I'll open the Discord afterwards. Okay. Let's see. Okay. So that is good. The change in kinetic energy. Let's go to part B here. Last part for this one, which says, consider the case where a new block is dropped and it collides with the top of the cart. The new block slides along the cart during the collision, but does not slide off the cart. The time interval for when the new block collides with the cart and moves together to the cart is delta t. During delta t, there is a frictional force that acts between the new block and the cart. Indicate whether the x component of the momentum of the new block cart system increases, decreases, or remains constant during delta t. Wow, this is tricky.
You're not that guy, pal. Trust me.
Man,
you're not that guy.
Why'd they do this to us? This is a tricky part. Okay, here. I'm gonna put this down here in like part B. And then don't worry, I will post the PDF for all of this, so you don't have to worry about taking screenshots and stuff. And also, this entire live stream gets recorded on YouTube, so you can always go back and cycle through it. I think you can even right now, you can kind of use the DVR feature to rewind on things and then come back to live if you need to see something repeated again. Okay, so let's take this picture of what's happening. So this is this. And then it's kind of like, it says it slides a little bit. That's crazy. I guess it would. Nothing ever sticks immediately. There's always a little bit of slip. Okay. No. Okay, so what they're saying is we drop this block onto here, and this thing will start to slide a little bit backwards as this is moving forward. And then eventually, but it doesn't fall all the way off because that would be bad. But it'll slide a little bit and then it'll stop. And they want to know what's happening to the x component of the momentum during that entire time point. Oh, okay. Again, so momentum only changes if there's an external force. On the system. The system in this case is the block that got dropped as well as the block that is moving. So you have two blocks. So we have to think about the force acting on the whole system, like on both of these. So it is correct that this thing being let's assume there was no friction. Let's say this is like a completely slippy surface, right? If you dropped this block on here, this thing would just whoosh right past it. This would just slide right underneath it, and this top block would fall to the ground, and it wouldn't even recognize that it got hit. But there's friction. And so what happens is when this block that is falling collides with the moving cart, it is going to experience a force of friction. And what's going to happen is this block is going to feel a force of friction to the right. Let's maybe call it, let's call this thing 1, I guess, right? Let's call this like thing 2. So the force of friction acting on this is actually coming from the moving cart. And this is what I would say like F12, which is the friction. But by Newton's laws, we know that there have to be pairs of forces whenever you have things acting on each other. So in this case, block 1 exerts a force of friction on block 2, which causes this thing, yes, to have acceleration, pointing to the right, and that should make sense because when the block was dropped originally, it had no velocity in the x direction. But at the end, it does have velocity in the x direction, which is equal to the same velocity as the cart. So this top block does have to experience acceleration to the right. So we can say like the acceleration of a block 2 is going to be to the right. However, because it's a pair of forces, block 2 is also going to exert an equal force on block 1, which we can call F21, which is also friction. So when you think about the force diagrams, this one will have a force to the left, this one will have a force to the right, but if we were to look at the whole system, these two forces are equal and opposite, and so the net force is 0. So this is kind of the tricky, mind explosion part of this question, which is that even though there is friction, there is a force, on the entire system, those two forces cancel out, and there is no net external force that is changing the momentum here. In fact, all that's happening is when the block initially drops, it's going to go from having a velocity of 0 to eventually having a velocity equal to the two things together. But so it is going to start speeding up, whereas the cart is going to start slowing down. Yeah. Okay. One sec. Let me catch up on chat. Let me make sure if I got stuff here. Okay, cool. Sensation. What's going on? Sorry. Okay. All right. Great. Does this make sense now? So what we're going to say here is that because momentum only changes if there's an external force, and we can say that the friction is an internal force. So total change in momentum is equal to 0. So when they were saying to indicate whether the x component of the momentum increases, decreases, or remains constant, you're going to say remains constant, and then your justification for it is that there is no external force on the system. Friction is acting to speed up the falling block and slow down the moving cart, but they cancel each other out so that the system as a whole does not have any change in momentum. Oh, thank you, Hampton. I appreciate it. Okay. All right, cool. So there you go. That is that all is that all of question 1? Yes, that's all question 1. So congrats, we got through question 1. This was kind of a heater of a question, honestly. And when I first saw it, I was a little bit confused at things. Work and energy can be applied even in rotational form. Okay, so that's a different question. We'll get to that. Okay, so there you go. That's question 1. Let's move now on to question 2. This one was a little bit tricky. And mainly because I hate when I see all these words start to scare me. There's so many words, and I'm like, physics is math and numbers. Why do we have so much words in this question? But okay. So a block of mass m, located here, is released from rest at position x equals 0 near the top. It makes an angle theta with the horizontal. The block slides down the ramp with negligible friction. At x is equal to 8d, it makes contact with the uncompressed spring. And then, so that's, I guess it's, yeah, that's in between here. And then the spring is then compressed, and the block momentarily comes to a stop at x equals 12d. Figure 1 shows the instance at which the block is at 0, 6, and 10. Man, dude, this problem sucks. What? They have three different pictures, but not even for like all the time points I wanted. I wanted at 8 And I want it at 12, but they give me pickers for 0, 6, and 10. Ugh, this is gross, but okay. Anyways, there's a spring. It's uncompressed here at 8D. This thing is up here at x equals 0. And then eventually it's going to collide with it here, and then it's going to compress it to its maximum compression, which will be when the block is at 12D. So this isn't even the maximum compression yet. And D measures the distance of the block from its origin. So when the block has moved an additional 2D to here, that's when the spring is compressed the maximum. Okay. Let's see. All right. Figure 4 shows an energy bar chart representing the kinetic energy of the block, blah, blah, blah. Okay. The spring and the Earth system. And then we have it at, all the different things. Great. Draw shaded bars that represent the kinetic energy, the gravitational potential energy, and the spring potential energy to complete the energy bar charts in Figure 2 and Figure 3 for when the block is released from rest at x equals 0 and for when the block is at 60, respectively. Shaded bars should start at dashed lines, represent anything that's 0 with a distinct line. Great. And the relative heights should represent the magnitude. Yeah, okay. So, let's see. At this time point, okay, the block is at rest, which means that there is no kinetic energy. So I can instantly just put a 0 here. Cool with that. Love it. Also, the spring has not been hit yet. So the spring should have no potential energy, right? I think the spring energy should also be 0 here. Let me double check. I have the answer key as well. Yes, great. Okay, cool. I'm not crazy. All right. So spring potential energy here is going to be 0 when it's at 0D and also when it's at 6D. The spring potential energy will be 0 because the spring has not compressed yet. It's just chilling. Great. Okay. They give us all the energies for situation 10. And something we need to remember, right, by conservation of energy is that the total energy needs to be the same. So let's figure out what the total energy is here. So this looks like 7 plus 2, which is 9, plus 3 is 12. So we could say that total is equal to 12 E naught. Okay. So in our first situation, when the block is chilling at rest, and the spring has not been hit or compressed yet, all of that 12E needs to come from potential energy, which is because this block is starting at a height. We don't know what the height is yet, but I know that the total energy has to be 12, so I can draw this. I know this is correct. Okay, now let's look at the case at 6D. Well, at 6D, I need to have lost some potential energy. I don't know how much I've lost, actually, because they don't tell you what this angle is. You do need to know what this angle is in order to know how much energy is lost from here to here. Pretty sure, right? Because I would need to know the change in the height. Because I don't... Or do they tell me that... Do they tell me that the potential energy is 0 at 12? Yeah, they don't tell me that. They haven't told me it yet. I think in later parts, they end up telling us that we're going to call gravitational potential energy when it's at 12. And then you can make some assumptions. So for now, I'm just going to say that the kinetic energy needs to go up because it's now moving, and the potential energy needs to go down, but the spring energy is still 0 because it hasn't been hit. But I still need this to add up to 12. So one convenient thing would be, okay, let's just put this up to 6, and then let's put this down from 12 to 6. And then this is technically correct.
Good job!
But I think for the purpose of scoring here, if you had this one a little bit low and this one a little bit high, you'd still be okay. The main thing they want you to show is kinetic energy goes up, potential energy goes down. And that they both add up to 6. So you could have done 5 and 7 or 4 and 8. That would have been okay as well. Okay. Does that make sense so far? What we got? Let's see. Part B. Okay. Says figure 5. If you had it 11 and 1, would you be fine? Yeah, well, no. I'll show you why. Because we say that the gravitational potential energy has to be at least 2 when it's at 10D. So do you see here? So because this definitely has less potential energy than this, the floor on like how low this could be would be like probably 2 or 3. So yeah, you couldn't do 11 and 1. Also from here, right? Oh, actually, this is kind of cool. So we know, right, as this thing starts going down further and further, its potential energy has to keep decreasing. So potential energy has to be in between here and here, right? Kinetic energy is a little trickier because some of this kinetic energy gets dumped into spring energy. So I don't think you can necessarily say that the kinetic energy has to be in between here and here. Yeah. Yeah, it's tricky. They try to get you, man. Yeah. Okay. I think that's okay to write it like that, though. As long as it adds up to 12, yeah. Great. All right, so, okay, now they finally give me the picture at 12D. So this is when the thing has compressed the most. And then the block is temporarily coming to rest. So at this point, we know the kinetic energy is equal to 0, right? Starting with conservation energy, derive an equation for the spring constant K. Express your answer in terms of m, theta, d, and physical constants as appropriate. Begin your derivation by writing the fundamental physics property. Okay, blah, blah, blah. Okay, so the fundamental physics thing is that conservation of energy. Great. And what I know is that the total energy... So what they want a thing for the spring constant. So 12E naught is the total energy. But let's think here 1 sec. Oh, we're allowed to use theta though. Oh, great. Oh, I love that. Okay, never mind. Then I don't actually have to do this. Okay. Let's come up with what in this case you only have potential energy from the block. So here energy is just equal to potential energy. And that's going to be equal to the mass of the block, which I think we're allowed to say m, right? So that's m times g and then times the height, right? Now you have to remember from a right triangle, yeah, Sensation's right. Yeah, don't dox people with their real names. You guys are okay though. All right, this height here is going to be equal to 12d sine theta. If we assume that this distance here is well, we're also I think calling this 0 potential energy. Do they do that? Where do they label that? Maybe that was at the beginning. Sorry, let me go find that. They have to tell me the potential is equal to 0. No, they don't do it there. Okay. Oh, but I do know it here. Look at this. So, oh man, that's annoying. You have to go for that. Okay. They eventually also give us a graph of what the spring potential energy is at all the different distances. And we see here that the spring potential energy is equal to 12E naught at 12D, which means, remember from before that the total energy was 12 at 10D as well. So if all the energy is in spring, that means at position 12D, they're calling gravitational potential energy 0, and then also the kinetic energy is equal to 0. Oh, we did say it earlier? Oh, I missed it? Okay. Where did I miss it? Oh, here it is. Oh, man. Oh, these people, dude. What? Dude, why would they write 0 instead of just saying 0? I was looking for the letter 0. Oh, the number 0. Okay. There we go. This is the key information. These motherfuckers, I swear. What? All right. Yes. Okay. Anyways, we're calling this 0. This is like our new h equals 0. So this position, this height here, is going to be equal to 12d sine theta. And that comes from trigonometry. Probably remember from trig, right? So if this is your hypotenuse, and then this is theta, and then this is the opposite, right? This amount is going to be 12d sine theta. So let's put it in there. 12d sine theta. Great. Love. Okay. Then at position 12, kinetic energy is equal to 0. Spring energy is going to be maximal. And we're going to say that potential gravitational energy is equal to 0. And this is equal to 1/2 k, and then x squared, where x is the change from its equilibrium. And we were told earlier that equilibrium is at 8d. Yeah, so this is delta x squared. So that's equal to 1/2 k, and then we could say 12d minus 8d squared. Because then this is the equilibrium. Yeah, I would have also, yeah, I would have just called it 0. It has to be called 0 at something, at some point, because otherwise none of this makes sense. Okay, great. So now I say that this total energy has to equal this total energy. And so we're going to say 12 mg d sine theta is equal to 1/2 k. So 12d minus 8d is 4d's, and then 4d squared is going to be 16d squared. Awesome. And then what the hell are we solving for? Solving for k. We just want k. Okay, great, cool. I could move the 2 over. Can't cancel any m's, unfortunately. Okay, so 24 mgd sine theta. And then that's going to be over 16d squared. It's equal to k. Well, one of the d's will cancel. And 24 over 16, that's an 8. So I get 3/2 mg sine theta all over d. Which is the correct answer.
Oh, yeah.
Nice, we did it. Good. Okay, there you go. So this is equal to k. So again, just set up the conservation of energy here. Set up the conservation of energy here. Do a little bit of algebra. You can solve for k. All right, let's see. Now things are getting really into the weeds. Figure 6 shows a graph of the energy of the system as a function of the position of the block from 8d to 12d. The spring potential is shown on the axes. Do the following. Sketch and label a line that represents the total mechanical energy for the block spring earth system as a function of the distance of the position of the block. Okay. Well, I know that the total mechanical energy, which includes gravitational, kinetic, and spring, that's constant. And that is always equal to 12. So we can just draw a big fat line here. Just be like, cool. It's always 12. Okay. Now in terms, so sketch and label, so this is mechanical energy. So this is, this is mechanical energy. They want the gravitational potential energy. Okay, interesting. Well, we know the gravitational potential energy is 0 when it's equal to 12. And then let's think. Oh, wait a minute. Do we know another position? Oh, we do here actually. Wait. At 10d, we know the gravitational potential energy is equal to 2. How much work needs to be shown to get the credit? I think, well, first of all, you need to state conservation of energy, and then you would at least need to show this equals this. And then if you get to here, I don't think they care too much about the algebra. Just show it. So it's not exact. So there are three things though, right? Because there's also kinetic energy here. So yeah, here's the key thing. LA243, you have spring potential energy, but you also have kinetic energy. So it's not just exactly like this, because that would be if there were only two sources of energy. There are actually three sources of energy. There's the kinetic, the gravitational, and the spring. Now, the gravitational energy will be linear with distance, because let's remember, so gravitational energy in this case was equal to mgd sine theta, okay? Theta is constant, mg are constant. So what you should notice is as d increases, so does gravitational potential energy. And so as well, actually, sorry, it's inverted, sorry. Right. Because d represents the distance from here. So sorry, it's oh man. Yes, this is 0. So as d increases, gravitational potential energy goes down. Okay. So there's a minus sign on this, I guess. It's 12 minus. Yeah, this is what it is. Or, no, in this case, it's going to be... One sec, let me figure this out. I think... Yeah, this should be like this. Well, let's use a different color for this. This happens here, and then we have this. Yes, okay. Because, yeah, okay. And then at 8D, which is right when the block has hit the spring, because the spring potential energy is 0, but it's just starting to go up, we know that kinetic energy then would have to be equal to 8. And then this would kind of probably follow some sort of weird thing like this eventually. For kinetic energy. But yeah. This is also dependent on what the angle is. The main thing here is that potential energy is linear with distance. So if you have 2 points for what the gravitational potential energy is, like I know at 10D it's equal to 2, and I know at 12D it's equal to 0, because that's where we define 0 gravitational potential energy, that if we connect a line between these two, that will map out what the gravitational potential energy is at all the other distances. Yeah. So, yeah. This is the correct way to eventually show the whole thing. Total potential energy, total mechanical energy is equal to 12, and then gravitational potential energy is linear and decreasing. And that comes from this. Say this is a linear relationship. Between mu g and d. Okay. And then, right, we're not including the third energy source, which would be kinetic energy. That hasn't been dropped in here yet. Okay. Does that make sense? Or do you want me to, I can re-go over some of these parts, because this was confusing, honestly. This whole question is kind of a mess.
Oh, brother, this guy stinks!
This whole question gives me a headache. Typical AP. Okay. Yeah. So, yeah, why is it linear again? The reason for that is potential energy is always equal to mg times the height, right? And the height is equal to d sine theta. And sine theta will just end up being a number. This is just a number. and that's constant, right? The angle at which this thing slides down is always constant. So that means that gravitational potential energy varies directly and linearly with the distance. In this case, it's a negative relationship because it goes down as the distance increases. As this increases in distance from its starting point, it starts losing gravitational potential energy at the same rate. And also because the force is constant. That is true. Yeah, you're right, Jorgen. In this case, it is. Gravitational potential energy is not linear in terms of time, right? Because things usually accelerate as they're falling down. But in terms of distance, it's just mgh. And so, if this changes by the same amount. All good. Oh, yeah, Jorgen. Yeah, we don't need to go into, like, that much. Yes. I know technically gravity is 1 over r squared if we want to get into, like, the big picture of things, but the delta r is so small, it's basically just linear. Yeah. Don't worry about that. That's a more advanced way to do that. Okay, cool. Here we go. Part D. Last part, which says indicate whether the speed v9d of the block at x equals 9d is greater than or less than or equal to the speed of v8d, and justify how your response is consistent with the energy lines or curves you drew. Okay. Well, let's see. We drew that. We drew this, right? Yes, where you use small g is just linear, right? Yeah, if you use the big G, which I don't think they do in AP Physics 1. There's another expression for gravity, which is this. It's m1, it's big G, m1, m2 over r squared. This is for, like, celestial things, or planets, or orbits, or satellites. I'm honestly so cooked with graphing and justifying my answers. Any tips? So in this question, G-Monkey, what I think was key in terms of the graphing is try to figure out points that you can just mark and then connect them. So in the case of the mechanical energy being constant, that's something we just have to remember from conservation of energy. And also, mechanical energy can sometimes mess with people. Mechanical energy isn't just kinetic. It's spring. It's also gravity. It's the total energy. I don't think it includes friction is the one thing mechanical energy doesn't include. Jorgen, you can double check me on that, but I don't think mechanical energy... Good. If you know something is increasing, how do you know if it's curve up or curve down or linear? Oh, you do use that? Yeah, okay. So that form of gravity is used for really big objects, not describing simple blocks going up and down on a hill on Earth. Yeah, we use mgh for stuff like that. Yeah, the big G mm over r squared, that's for, like, planets and stuff. So yeah, knowing whether this is curving has to do with whether it is a linear relationship or not. Let's remember, right? So for spring potential energy, remember that US is equal to 1/2 k x squared. Okay? So in this case, this is the distance. And you see how that's d squared? That tells me right away that potential energy has to curve with d squared. So it has to look like this. Because that's what a generic, like, y equals x squared graph looks like. Yeah, you don't include friction or energy loss due to heat as mechanical energy. Great. Good. Thank you. Thank you, 1A. So this is where something is curved. In the case where something is just straight, which is, again, linear, that had to do with, like, mu g equaling mgh. Yeah. When do I use gravity energy to find the velocity versus using the force of centripetal in non-elliptical orbit? I had a question like that and I couldn't figure out. Oh, interesting. So, yeah, if you have a screenshot of that question, so while we're doing these, if these are all easy to you and you're like, yo, GG's, at the end of this, which will probably be in the next 30, 40 minutes, we only have 2 more questions to go through. I will open up, like, an open office hours for you guys to just ask whatever questions. The website for that is here. I'll post the link here for you guys. This stream will go for, I have it planned for at least 2.5 hours. If there's enough demand, I'll keep extending it. But that website there, you can type in your username and drop a screenshot in, and then when you hit upload, they'll get put into the queue here. And these are questions that we might go through later. So good, yeah. This is a good example of a question we could do. And then this is another one. Let me see. What did Jay? Great. This is another great one. Yeah. So if you have any screenshots of stuff that, such as that one question you talked about, Blinding Storm, you can drop them in during the stream, and they'll get added. And then we'll go through and do them at the end of this, which should be in the next, I don't know, 40 minutes. Enthalpy? Yeah. I don't think they need to know enthalpy either. That's like chemistry stuff too, or like stat mech. So, what the hell? We are not. Yeah, we're not touching that. No, we're not doing that. Okay, so curved is when things like have x squareds and stuff in them. Straight is when nothing's being squared; it's just linear. And then you can get stuff that's inverse. So this is another like curved, but like also like inverse. And the case for this would be, for instance, I'm trying to think what you guys would do with this. Yeah, maybe the stuff with... No, because you're not doing electrostatics. Wait, what's going to go as one over R? Yeah, sure, maybe this. M1, M2 over R squared. So this is now something 1 over R squared. Okay, cool. Question, I think that's all. Well, we haven't done this yet, sorry. Okay. So they say indicate whether the speed of the block at V90 is greater than or equal to the speed of the block at 8D. Well, let's look here at what's happening. So we know that the sum of these two things plus the kinetic energy has to always equal 12. So again, if you suck at graphing and you don't know where to put things, just graph points. So I know that all of the energies have to add up to 12 because that's the total mechanical energy. So at 8D, I have a 0, I have a 4. That means this must be kinetic energy. And then what about here? Okay, well, this looks like I have a 3 and a 1. 3 and a 1. Well, it's actually slightly less than 1. It is so slightly less than 1. Yeah. This is 3. This is slightly less than 1. So this is going to have to be slightly more than 8. That's really shitty, honestly. Okay, but we could look maybe here as well. Let's see here. This would be 1 and 7, so that means this would have to be 5. And then what is this? This is definitely 2 and 3, which is 5. So this would have to be 7. Yeah. So I think actually what happens is kinetic energy does some weird stuff, actually. It's going to look kind of like this. And then kinetic energy, right, eventually has to go to 0. When we hit the end. So I think what you want to say is that V9D is technically more than V8D. It's working. It's not working on the it should be working. One sec. One sec. Oh, you're right. It's not working on the big chat. Yeah, let me fix that. Oh, man. Give me a second. Let me figure that out. I don't know why that's not working. Yeah, he's talking about like in this form it's frozen. Yeah, I do see that. Maybe we just haven't had that much chat on here, let me select this. There we go. Okay. Yeah. That should be fixed. Yeah, one sec. Let me fix this. There we go. Okay, now it's back. Okay, what was part C? Okay, part C was here. And this was asking for us to sketch and label this graph to show what the total mechanical energy was, and also the graph of the gravitational potential energy. That was the two things they wanted us to graph for part C, Lawson. And then part D was just seeing, okay, based on our graph here, is the velocity at 8D more or less than the velocity at 9D? And so what we had to show here was that, well, if this is linear, then this should fall exactly here on 3. Do you see how this spring energy is technically a little bit lower? It was just drawing the energy loss on you. So that means the kinetic energy here has to be greater than the kinetic energy here, because these two add up to 4. These two add up to like 3.9, and then whatever's left has to get you up to 12. Can't you just say that since there's less gravitational potential energy, there's more kinetic energy because the spring force is not big enough yet? You can talk, oh man. The problem is eventually the spring force becomes enough. Like, for instance, here, right? Here, yes, you have less gravitational potential energy, but now the spring force has increased by so much that your kinetic energy is really starting to fall. Yeah, so it's a little tricky, a little convoluted with how that works. I guess you could do it numerically. We could go through and figure it out with the numbers, but I think all they want you to do with justify is to just look at what your graph was and to tell and to say based on the graph which one should we have gotten. And actually I'm looking now at the grading part. It's actually pretty cool here. This is one of these cases where they won't penalize you if your previous part is different. So if we look here at the official grading rubric, they say if you indicate that V9 is greater than V8 because the sum of these at 8 is greater than the sum of these at 8, some of these at 9, then you're good.
My man.
If you say that V9 is less than V8D because the sum of this is less than what it is here, then that's also correct. How would this graph look if the energy was in quantum space? No. Don't choose violence this morning, Tabul. So, yeah, that's a couple levels above Physics 1. So, in general, all they wanted you to do was based on the graph you had drawn in part C to make the observation that kinetic energy and the sum of these two things has to equal 12. And so if the sum of these two things is going down, then kinetic energy is going up to make up for the lack of getting up to 12. If the sum of these is going up, so say for instance, we screwed up and we drew our graph like this for gravitational potential energy, then we would say that the kinetic energy is less at 9D. We would say it's lower. And according to the rubric, that would be okay based on what our other thing was. What is quantum space? Fancy probability land of things. It's quantum space. Scary land. Yeah, where time stops working. Yeah, everything's a lie. It starts bending. Cool. All right, so I think that's all we had for part D, so good job on question 2. Let's move forward to question 3. Okay, it says students are investigating a balancing system using this setup. There's a meter stick that can pivot. You have a spring scale. You have this block with this hook, and then you can hang it at different points. And they said the students are asked to take measurements that will allow them to create a linear graph whose slope could be used to determine the mass of the block. Describe an experimental procedure to collect data that would allow the students to determine M naught, include any steps necessary to reduce experimental uncertainty. Okay. So this is kind of getting back to an application of torque. So what we know is that if I were to hang a block, let's make a little saw block here, because this is the pivot point, you would have a torque that is trying to pull this side down, and then you would have a torque from the spring scale that is then keeping it level. So by placing this block at different positions, you're changing the torque, right? Because we know that torque is equal to, I think you guys learned it as RF sine theta. In this case, theta is 90 degrees, so this whole thing is just 1. And so as you increase the radius from the pivot where you're putting this block, that causes more torque to try to pull this thing down. And thus, you're going to have more torque from the spring scale, or more force from the spring scale, to keep it level. Yeah. Yes, Blastian, you're all getting 5s. The fix is in. You're all getting 5s. Okay, so describe an experimental procedure. You could say, move the block to different positions, and then read the force on the spring scale. Great. Is it fixed? I think it is fixed. Sensation, right? Yeah, torque is satisfying. I do like torque. Torque's great. Okay. So then if you wanted to graph this and show how we could determine m naught, I think we want to let's use some equations, right? So the torque from this, right? We would say like torque from the scale. That would always be equal to the force of the scale times the distance, which in this case would be 0.5, right? Cool. And then the torque from the block as in rigged. Okay. The torque on the block is going to be whatever the position is here. Maybe let's say the position minus 0.5, because I think we would be reading this, right? So I'm going to say position, which we'll say x, minus 0.5, and then that would be times the force that's pulling it down, and that force would be equal to m naught g. Okay. And then if this thing is level, then these two torques have to equal each other. Yeah, exactly. There you go. Welcome. We'll be doing open questions after I finish the FRQ. So next 20-30 minutes, I think. We're almost done with this one. Okay. So you can say torque scale is technically equal and opposite to torque block. Technically, this is a negative torque because it's pulling clockwise, and this one's pulling counterclockwise, but so we could say F, let's say Fs times 0.5 is equal to x minus 0.5 m naught g. So then, if we were to move that over, Fs is equal to x minus 0.5 over 0.5 times g, and then this is times m naught. Okay. So let's think how I'd want to do this. Maybe let's remove the 0.5. I don't really like the 0.5 actually. Let's just say that this is actually the distance, because otherwise the algebra gets actually kind of ugly. Let's just call this like delta x times m naught g. I think that's a better way to write this. Because when you want to do something where the slope is equal to what the thing you're looking for, you want to just have a bunch of coefficients in front of one thing that you're varying. This is what we learned, right? Y is equal to mx, and then I guess like plus b or whatever. So this is your slope. So you want to graph this versus this. If you graph this versus this, whatever is here will be the slope, and that's sometimes what you're looking for. In this case, we're trying to figure out what m naught is based on here. I know this spells out mog, but it's m naught g. So if I were to graph fs versus g delta x, and dividing by 0.5 would be the same thing as multiplying by 2. So I'm going to say 2g delta x times m naught. Then this is the slope. And then this is my y. And then this is my x. They love putting one of these questions all the time. All the time on these exams. Is experimentally what would you graph blank versus blank in order to get an expression where the slope is equal to what you're looking for. So in any of those cases, set up equations. Sometimes it's like this force equals this force, or like this distance equals this time. And the thing you're looking for, you want to have being multiplied by the thing that you're varying. So in this case, we're varying delta x, which is the distance this block is from the rotation point. And we're measuring the spring force. And that's what happens whenever you're doing a graph of y versus x. You're saying that if I move this around in terms of x, what happens to it in terms of y? And that's how you get graphs. Graphs are just showing that relationship of if I do something to x, what do I get out for y? So in this case, it's if I move this stuff around, so 2g times delta x, and then I measure what I get for fs in terms of y, the slope between those two things will just be my m naught. So you could do that as well. So actually there's a bunch of different correct answers for here. So this would be one way to do it. The other way to do it would be this. You could say that this is y, and you could say that 2g m naught is equal to the slope. And then you could also say that this is equal to delta x. So you could directly just graph fs versus delta x. But then when you get the slope, you would have to do slope divided by 2g is equal to m naught. If you do it this way, so if you graph fs versus 2g delta x, like if you bake in the 2g already into what you're graphing for x, then the slope is exactly m naught, which is what you want. Yeah, exactly. Yeah, 8-bit has it right. And then Lawson, yeah, the 2g came from this. I divided by 0.5. Because the torque here was F times 0.5. And you divide by 0.5, you multiply by 2. Yes, they also will do that too, 8-bit. You are right about that. So it's about recognizing. You want to recognize the thing you're looking for needs to be multiplying by something you're varying, and then it's isolating for like, how do I get to that? Yeah. Okay, but I think in the answer choice, they'll accept you could have done this or you could have done this. But when you do this, you need to say that m naught is now the slope divided by 2g. That's the only key thing you have to do. Okay. Let's see. Okay. Oh, here's another one that comes up. Okay. They say the angle... Okay, so this is a completely different situation where you have a wall. Oh, I see. And then what they do is they're changing the angle at which you're attaching this. So you could attach it here, you could attach it here, you could attach it here, you could attach it here. And that makes a different angle between this with the meter stick, I guess, here, which is... And then also you could change this, I guess, as well. Oh, very cool. All right. the students use the spring scale to measure the tension required, and then they're measuring this. They're measuring what Ft is here. To hold this thing up. Because this is going to have a couple forces, right? This will have some force of gravity pulling it down, and then additionally, you're going to have a normal force pushing from the axle onto the meter stick. And then those forces all balance each other out. But they're not asking you to figure out those forces. They just give you, for all the different angles, what is the tension. Cool. And then they say, okay, here, the student correctly determines the relationship between... This is also torque, yeah. So, yeah, if you actually had to set this up, this would be a sum of forces question, and then also a sum of torques. So you would have to break this up into, for instance, like ftx would equal negative ft cosine theta. fty would equal ft sine theta. And then you would have force of gravity is equal to negative mg, right? And that's in the y hat direction. Or here we could just say fgy. And then additionally, you would have a normal force acting on the axle. So we would say F axle in the x direction, and that would be unknown. Yeah. In this scenario, would the normal force of the axle have a negative vertical component, or would it be purely horizontal? I think it depends. Well, you're actually interesting. Okay. No. It shouldn't. I don't think it'll have a normal force, because this tension will adjust to keep this thing level. If there was more tension than there needed to be, then yes, then you would have a normal force on this axle either pointing up or down. I'm pretty sure. Because and again, this is not related. You don't actually have to do this for the question, but if you wanted to do it, you would have sum of forces in the x direction. Would just be F axle minus ft cosine theta. And then sum of forces in the y direction would be equal to ft sine theta minus mg. And then you could also do the sum of the torques. So actually, yeah, wait, I think you could actually also have plus force normal of the axle. Yeah, wait, I think you could actually. But then this would come from sum of torques. You would have, because you would use this as your pivot point, you would say Fg times 0.5. If this meter stick is 100 centimeters, gravity acts halfway through it. And then this minus Ft sine theta times, I think in this case, 0.6. This would also have to equal 0. So there you go. So then you would have 3 equations, and you have 3 unknowns, right? F axle x, F axle y, and then Ft. You'd also have to know theta. Yeah. You could also get theta. I assume they would give you some dimensions here for things. Would Ftx be equal to normal force of the axle if it's in equilibrium? Yes. Although, I think you could still have... I think you still could have y... The axle could still have a normal force to the y direction, right? I think it could. Oh, wait. If it's flat, then no. Probably not. Yeah. Yeah. Okay. But that's beyond this. You don't have to... Don't worry about this. This is like extra credit. Here, I'll say this is like extra credit. Extra credit. If you really want to go through this. You don't need this for the question. And this is something that happens definitely in higher level, like engineering statics. This, if any of you guys ever want to go to engineering, they love doing these questions. It's called statics. There's a whole class just dedicated to doing this type of stuff. It's called statics. Yeah, and the axial forces are confusing. I don't think you need to do these for AP Physics 1. You're okay. You're safe for now. Okay. Okay, so they determine ft is equal to this, and they create a graph with 1 over sine theta plotted on the horizontal axis. Okay, this is cool. So again, we're doing ft yeah, exactly, but yeah. So this is going to be 5mg over 6, and then this is times 1 over sine theta. I think this is kind of what 8-bit was talking about. Sometimes they're going to give you the equation, and you have to go figure out what the slope means. So in this case, they're graphing this on the horizontal axis, right? So this is being graphed as x, right? And then indicate what measured or calculated quantity could be plotted on the vertical axis to yield a linear graph whose slope can be used to calculate an experimental value for the mass of the meter stick. Okay. So a couple things you could do. You could just graph. I think there's a couple answers for this. So, like option 1. You could graph ft versus 1 over sine theta, and then this would be your slope. So 5mg over 6 would be equal to your slope. So if you wanted to figure out the mass, now you have to tell them that, oh, okay, then m would equal whatever I got for my slope times g over 5. Oh, is it 5g? 5? Oh, this is a 6, not a g, sorry. My g's and 6 is looking the same. Okay. Let me fix this. There we go. Slope times 6 over 5g. That's what m would equal to, right? If we multiply this over 6, divide by 5, divide by m. That's one way to do it. Option 2 is we could... So in this case, this is y, this is slope. And this is kind of another fun way to do it. Is you can bake in this part on this side. So I can multiply this by 6. I can divide by 5. I can divide by g. And now I could graph this versus this. And then this would be the slope. So the other option is you could graph 6ft over 5g versus 1 over sine theta. Then m would be equal to the slope, and you wouldn't have to do anything else. No, I think m. Wait, because we want to figure out what m. We want to figure out what what the mass of the meter stick is. Right? Ft is equal to 5,6 mg 1 over sine theta. We're trying to solve for m. So m is going to be the slope. Or something with m is going to be the slope. Oh, in option 1. Okay. Oh, yes.
Good job.
Thank you. I did fuck that up. You were so right. Thank you. Yes. This is slope 6/5 over g. Yeah. Multiply by 6, divide by 5, divide by g. Very good, Blinding Storm. Yeah, good eye. Yeah. So that's one way to do it. Then this would be the other way to do it. You could bake this into graphing for y versus x, and then m would just be equal to the slope. Okay. Your teacher barely, yeah, unfortunately, fluids got added last minute last year, basically. And so a lot of physics teachers don't, especially AP Physics 1 teachers, don't have a lot of experience with teaching fluids. and kind of skipped over it. I think fortunately they're not making it that heavy of a component during the exam, but the next question will be fluids that we're going to go over. And so I'll explain a little bit of fluids. I'll explain a little bit of what you need to know with fluids. And then if you guys have any practice AP exams they gave you with fluid questions, please submit them here to the queue. There you go. This is a cool one. If you submit any fluids questions, I can go over how to explain them here. Yes, it was the last question on the FRQ, and we are going to do that. That is the last question we're going to do. Okay. The next thing they want you to do is use the values you had here. This is annoying. To have to do all this. And they want you to graph what you got. Oh man. Fluids make me cry fluids. Oh dear. Oh dear. Okay. So to get this, I'll do a couple of the points and then I'm just going to copy paste what they had from their answer key because I don't want to waste time showing you guys how to calculate things. It's kind of. All right. So you want to graph what 1 over sine theta is. So first thing you got to do, make sure your calculator is in degree mode because these are all in degrees. And so even though they give me theta here, I want to graph of 1 over sine theta is. So, and I think do you get a TI-84 in the exam? I think you get a full calculator, right? In that case, you could actually do it. Well, here, I'll do it the manual way, then I'll show you some fun tricks for it. So you could do 1 over sine 22 like this. And you could write this down by hand. So this would be 2.667. Oh no, dude. Okay, fine. 2.67, and then you could do. Let's just do another data point. Let's just do 1 over 45. That's gonna be 2 root 2. So what is that? And you get Desmos. Okay, cool. So that's 1.414. Yeah. So there you go. So those are 2 data points you could have. And then we have FT. Let me see which way they do it. So I make sure when I'm including it in the graph, we don't have to reinvent the wheel. They just graphed FT. Okay, that's fine. So they did option 1. So if we graphed FT versus that, then I have 2.67 and 21. So that's here, this is 2.5, this is 3, so wait, 1, 2, 3, 4, 5. So, and then, you have to label this. And that's going to go all the way from 8 to 21, so 1, 2, 3, 4, 5. Let's do it by 5s. Yeah, let's say 5, 10, 15, 20. Put the table in the Desmos and it gives you the slope, so you don't have to do it by hand. Okay. Can you just drop this in a Desmos? I know how to do it on the calculator here, but this is probably old school and ancient for you guys. So let's just do it on Desmos. I'm cool to do it on Desmos. Table, cool. Oh, that's super handy. Okay, but then I have to copy this in by hand though, right? Unfortunately, they don't give you just ChatGPT to OCR this. That would be super nice. Still gotta type this in by hand. Kind of annoying. Let me grab what the data. So I can grab it. Okay, so we had 22. Oh, but then you need to do the sine of it. So you have to say sine of 22, and then does it recognize this? Putting degrees? Probably not actually, right? Maybe you gotta do this. Donde está degrees? No? Okay. You're not cooked, dude. Just slightly roasted. Yeah. Yeah, it's super annoying, honestly, to have to do this, but whatever. Okay, sine 36. Sine I'm just curious in Desmos if there's an option for here to do it in terms of degrees. You would hope it does. Well, let's see. 21, 17, 13, 12, 8. Tool button. Thank you. There we go. Okay. Or maybe this. Oh, there we go. Degrees. Yeah, make sure you hit it. Sorry. Let me get my head out of the way. There it is. So here at the bottom right, guys, it says degrees. Right here with the tool thing here. Top right. There you go. Top right and then bottom right. Hit degrees. Brilliant. And then here was the key thing. We had to graph 1 over this, right? Oh, that's super annoying. Do I have to recopy this in every time? Oh, man. There we go. Okay. There we go. Okay, cool. That's super handy. Thanks for the tip, whoever put that in my chat. Great. I was going to do it with the TI-84, but y'all get Desmos. This is hella nice. Okay, cool. So there you go. There's a graph. If you wanted to kind of set what your... I mean, to have like some slightly nicer axes, I would say that X goes from 0 to... What do we have it on the graph as? 0 to 3. There you go. So there you go. That's the graph. That's what it looked like. Does this exam really matter? Yes. Yes, it does. Yes. You want to get credit for this exam. It'll help you out so much in college if you do well on it. Because, man, trust me, you don't want to take physics with college professors. It's like 200 kids in a lecture hall. I teach it at UCLA. I teach college physics there. And it's pretty brutal. If you can get it out of the way with an AP exam, trust me, it's hella worth it. I mean, yeah, you don't have to submit it if you don't want to. Okay, so there you go. So there's the equation we got. I will include some of the... Here, I'll include the Desmos stuff in here. Yeah, if you have to take it anyways for your major, yeah. It's also good practice just to take it now. And learn it now, because when you have to learn it the second time in college, it'll be a breeze. Yo, you should admit me to UCLA. I'm unfortunately not on the admissions board. I just teach there. But if you get me for your class, yeah, okay. You should totally take my class. I get pretty decent reviews. Okay, there you go. So there's the graph. Beautiful. And then, okay, calculate the experimental value for mass. Okay, great. So here, this is our slope. But we used option 1. So slope times 6 over 5g. That should equal to m. So let's pull out the calculator. So 6 over 5 times 9.8. Times, what was that? Times that 7.89? One sec. I think they got a mass of 1. I'm not going to get a mass of 1 here. We did the first way. We got a slope of 8.4. This got a slope of 7.9. Oh, and I forgot to put the G on the bottom. Yeah, my bad. There we go. Much better. I did it wrong, Nikki. You're so right. Yes. Sorry. It's 6 divided by 5 times 9.8. It depends. I didn't have to take physics 1. I went straight into... So I retook Physics 2 because I got credit for Physics 1 and Physics 2, but they wouldn't let me take Physics 3 until I had gotten to at least vector calc in math. So I retook Physics 2 just... So I was taking some physics as a physics major. Okay, there we go. All right, that times 7.9. Beautiful. Okay. Okay. So then you get m is equal to 0.977 kilograms, which I think is pretty close. They wanted 1 kilogram. Close enough. Okay. My mom wants me to sleep even though it's 7 p.m., dude. What? What? Who's going to bed at 7 p.m.? Excuse me?
Oh, no.
I think maybe they want you to like try to go to sleep at 7 p.m. Try to start trying to go to sleep or something. Okay. Yeah. Calc PC is gonna be oh no. Yeah. Is Calc PC tomorrow as well? Okay, question 3, we're done. Let's rock and roll through question 4. This shouldn't take too much. This is just fluids. Okay, in scenario 1, a swimmer holds a block of mass m in a fresh water with density ρ1. The block is released from rest and accelerates upwards with an initial acceleration a1. It takes you 3 hours to go to bed? Excuse me? You just stare at a wall for 3 hours? BC's on next Monday. Okay. Well, I'll recommend, hey, if you guys ever want to get help with BC Calc, if you got questions, come by the streams this week. So again, on that website I sent, actualofficehours.com, we have a streaming schedule, and I have more streams throughout the week that you can come by and ask calculus questions. And I'm happy to help you guys with calc as well. I do a lot of AP calc. So yeah, that's brutal, dude. Biochem and physics back to back. Okay. Then they say in scenario 2, the swimmer holds the same block, but with a density ρ2, where ρ2 is greater than ρ1. And this is in salt water. Okay. I don't know if you guys have ever noticed the difference between like swimming in salt water versus swimming in fresh water. You float more in salt water. It's easier to float. If you ever go to the Dead Sea, which is somewhere out in Europe, the Baltic or whatever, it's one of the saltiest seas out there. You can actually just float without even doing anything. Your body will just float in that water because the density of the water is so dense compared to regular fresh water. The reason why this comes from is a thing called buoyancy. So buoyancy is a force that propels items in water, items in liquids upwards. And what you learn there is that the buoyant force is equal to rho v times g, where this is the density of the fluid. This is the volume displaced. And then this is, of course, gravity. So all I wanted you to do here, I think for this is actually a really, really chill part here, is they say, indicate whether the acceleration in situation 1 is greater than or less than the acceleration in situation 2 by writing the following. So what you end up saying here is that the acceleration in situation 1 is less than the acceleration in situation 2. The reason for that is that in situation 2, the swimmer is holding the same mass in a denser liquid, and the buoyant force is linear with the density of the liquid. So if you're in a dense liquid holding something, that liquid wants to rocket that thing up faster than if it was in a low density liquid. That just has to do with, I think this is called Archimedes' principle. So yeah, that's why. So it says reference all forces, use qualitative beyond. Okay, you could just say that like force of gravity on both blocks is the same because they're both the same mass, but the buoyant force in ρ2 is greater than rho 1. Yes, that is the technical definition for buoyancy. Jorgen, you are correct. I just tell the students how to remember it. It's just the volume you displace times the density of the volume that you're displacing times gravity. It's really it's equal to the mass of the volume, mass of the liquid you're displacing, because that's what rho vg is, or like the gravitational force on the mass. Okay. So then they say this is why they were pretty soft on the fluids part of this exam. This is not very in depth at all, and I think they were being nice. They probably won't be as nice this year because they know you've had an extra year to get adjusted to learning fluids. But this year they were pretty chill on the last part here. So they said, starting with Newton's second law, derive an expression for the initial upward acceleration in terms of m, v, rho, and all the constants. Okay, great. So this is all you had to draw. So if you have a block of mass m, you're going to have the force of gravity pulling it down. And then you're going to have the buoyant force trying to float this thing up. And that's going to be equal to rho vg. So then the sum of these forces... Good. Yeah, okay, that's a very good question, Lizzie. So in that case, it's just equal to the amount that is submerged. And I'll show an example for that. In this case, we assume the whole thing is underwater. So in this case, this is going to be rho vg minus mg. And the sum of those forces is going to be equal to ma. So you can just say the acceleration is equal to rho vg minus mg all over m. That's all you have to do for that, honestly. It's pretty chill. And then bro, my teacher didn't test us on fluid and oscillations. What should I do? Stick around. I might go over some quick fluid. There's not that much you need to know for fluids. It's really this. It's the flux conservation one, and then do you guys have to do Bernoulli's equation? Did you learn Bernoulli's? That's the only other one you really gotta know. But we'll get to that. Okay. So, and then one second. So Lizzie, let's say for instance, let's say example. Let's say something was only like half submerged. Okay. Oh, you learn Bernoulli's? Okay, then cool. All right. Yeah. Let's say this thing is a block. Okay, let me do this in a different color so you guys don't get confused. It's not part of the whole thing. Okay, example. And then actually I need this to be solid because it's not full of water. Let's do this. Okay, there we go. Okay, and then let's say this is the water level. And then let's say this is a cube of okay, length is equal to 1 meter. And let's say the height that is submerged, and then let's say h submerged is equal to, let's say 0.25 meters. And here's actually kind of the cool thing. We could figure out what the density of this object is, like how much of it floats. I'll show you how you can do it. It's actually kind of fun here. And let's say rho of the cube is unknown. But you do know also that rho of the liquid is equal to, I think, it's 1,000 kilograms per meter cubed. Yeah, simple harmonic motion is on there. Yeah. Good, yeah, I'm going to show you right now with the force diagram. Okay. So let's think about this. So let's look at the sum of the forces. So you're going to have the force of gravity pushing down in this thing, right? Which is going to be equal to the mass times gravity. Now, the mass of this whole thing, right? That's going to be equal to rho of the cube times the volume of the cube. So L cubed. And then times G. So that's the force of the gravity that's pulling it down. Now, the buoyant force only comes from this amount. In this case, we got force gravity pulling down. You're going to have buoyant force pulling up. And the buoyant force is going to come from this. So we can say that force buoyant is equal to rho of the liquid that it's in times the volume of liquid that is being displaced times G. The volume of liquid that's being displaced, if this is a cube, this is going to be equal to L squared times H. Right? Because it's L this way, L deep, but it's only H high. Yes, and we assume it's floating. Yeah, let's assume it's at equilibrium, it's floating. We can figure out what the density of this thing is. So then I set these two forces equal to each other. I say, okay, FB is equal to FG. So that means rho L squared HG is equal to rho C, L cubed G. And we said L was equal to 1 and H was equal to 1/4. So, whatever. That's 1. And then rho of the liquid's 1,000. So you'd have 1,000 times 1 squared times 1/4 squared. And then the G's would cancel. And then that's equal to the density of the cube. Again, times 1 cubed. And so you would get that the density of the cube is equal to 1/16 times 1,000 kilograms per meter cubed. So the density of the cube is 1/16 the density of the water, and that's what causes it to float with only 1/4 of its part like submerged. It's all about just setting up the force equations. So gravity considers the whole cube. I don't care how much of it is above the water, below the water. Gravity acts on the whole thing. Buoyant force only acts on the amount of volume that is underneath. And the amount of volume underneath, in this case, was L by L by H. How do you know Fg is equal to the third equation? Oh. In this, okay, so force of gravity is mass times gravity, but this is mass of the cube. And the mass of the cube is equal to the density of the cube times the volume of the cube. Yeah. And so it's not moving, right? Which means that all the sum of the forces all have to equal 0. So the gravity that's trying to pull it down has to be equal to the amount of buoyancy that's trying to pull it up. Makes a lot of sense? Cool. Right. Yeah, in this case, this one is where it's fully submerged, okay? This case right here, where it's fully submerged. Now, the force of gravity pulling it down is just equal to mg. But the buoyant force is going to be equal to the entire volume. So we'd say the entire volume times whatever the density of the fluid is times g. So, and if I wanted to do these just in terms of densities, this would be the same thing as, right, let's say rho of the cube v cube g. And then this would be equal to rho of the liquid but it's still v of the cube times g. So something cool you should notice here, if the thing is submerged and it's not sinking and it's not floating, like if it's staying constant, then that means that the density of the density of the liquid it's in is equal to the density of the cube. Yes. Yeah, you're right, Jorgen. Yeah. Rotational momentum. Yeah, there was no rotational momentum on this question. It's kind of whack. You're all getting 5s on this exam. I believe in it. Yeah, you're all going to do it.
Oh, we're so sorry to hear about your brother.
5 big booms for all you guys.
He gets 5 big booms.
5 big booms for a 5 on the AP exam. That's what you guys are going to do.
Oh, no.
Okay, anyways. So, yeah. This is the main thing. Buoyant force is equal to this. Buoyant force depends on the density of the liquid it's in. Gravitational force only depends on the density of what the thing is, the material. Yeah. Is fluid one of the more popular topics since it's only a few years old? Yes, I can go over experimental procedure one more time. Sure, Becco, I got you. Is fluid one of the more popular topics? So it's not. It's one of the least popular, but it is increasing. So this was last year's exam, which was the first year they did fluids, and this was the only fluid thing I saw on the FRQ. And it's very basic. It's just buoyancy force. They were really nice this year. I'm guessing, sorry, this year as in 2025. I'm guessing for the current year, 2026, they're going to put more because they assume that you've been taught it a little bit better. Teachers were really blindsided by this, and it's why I understand that a lot of you are complaining that your teacher never went over fluids or oscillations. It's probably because they've never taught it before, and this only changed a year or two ago, so it's kind of like, so same density if it's not accelerating. Now if it's accelerating, how do you figure out which density is greater? If it's sinking, then FG has greater density, but if it's floating, FB is greater. Correct, yes. So if something is sinking, then the density of the cube, right, this has to be greater than the density of water. And this also should make sense, right? Have you guys ever done like the oil and the water in the beaker? What is this, it's like oil, beaker, water, density thing. Like this, right? You guys ever do this little cool little project or something? I don't know. Something like this. These are different density fluids, and so the ones that have lighter densities sit on top of the ones with heavier densities because, yeah. Yes, Tim, yes. So that's another example here of if something has a higher density than the fluids, then the fluid it is in, it will sink to be below that. If it has a lighter density, it will float upwards. I'm hoping you all get 5s. Okay, Becco, you wanted to help on the... So, okay, this is done, I think, at this point. For all the questions for this. This was a side example we did. And then this one, they were just saying, oh, yeah, reference this. Yes, you could say that for part C here. You just say, like, if rho is bigger, so is A. And that makes sense. If the object is in a higher density liquid, it will have a higher buoyant force, and that will cause it to accelerate faster to the top. You're not all failing.
Oh shit, not good.
Okay, for the experimental methods one, Biko, you were asking about this. My general strat when you're trying to do, because I know these things are really annoying. They're not super intuitive all the time. Look at what things you can vary and how those relate to things that you're measuring. So in this case, when this question was given, they said we had a block of mass M and we had all these different positions we could place it at. So when they say, like, what should I do in order to figure out the mass of the block? Well, you only have so many options, and the only option is really to just hang the block at all the different mass points. So if you want to consider, before you even know what you have, you should remember that concepts like torque depend on the mass of what the block is. So you probably want something where you're changing the torque on one side and you're measuring what that change does on the other side. Yeah. General advice for the FRQs, I would always look through all of them first and go after the ones that you know you can do first. They are very generous with partial credit on this. Just looking at I have the grading rubric for this one. So you never want to leave a question blank. Never do that. Never leave a question blank. Always write down something. But that being said, you want to make sure, go through it. If you see stuff that you instantly recognize, like, oh, I could do that, I could do that, start doing those first. If you're someone who doesn't like this experimental question ones, save this one for last. Just be like, whatever, I'll just do it last. Like, don't freak yourself out over it. I'm gonna pray for you. You're good. That's my general advice, and that's like with any test taking type of advice. Pacing yourself on a timed exam is very important, and so going after the easy ones you know you can knock out first, so that you don't blow through all your time on the hard ones and then have no time to do the easy ones. Yeah. Okay. So that's this for the FRQ stuff. I'm gonna go through the questions you guys have submitted screenshots to, and so this I'll post. I'll send out an email to all the students, but I'll also post this link for this in the recording for this that shows up. But okay, what's the slope for the experimental design one? In this one we did this. You had two options, so you could have done option 1. One sec, where was it? Yeah, you had two options. You could have chosen to graph this as y and this as x, and then your slope would have been 5 mg over 6, and then solving for m would have to be the slope times 6 over 5g. Or you could have taken all of these parts that aren't m, and you could have thrown them onto y. And now you could say, oh, I'm going to graph 6ft over 5g versus this. Yeah. Oh, I appreciate it, Charlie. Okay. All right. I'm going to go through the queue. I'm going to dump this link for you guys. And I'll hang around at least for the next hour, maybe 2. Blah, blah, blah. So, where did I put that? There you go. One sec. There it is. I'm going to pin that. No. Come on. There we go. And then pin. So there you go. That's the link to submit questions. And then I have kind of a fun little way of choosing questions, because otherwise it would be like first come, first serve. We do a little queue system here. So if you really like your question, you can always upvote it every 3 minutes, and it'll get like more votes. But here's I know gambling is the way that we decide things in this world sometimes. So we can go do that. We're going to go see whose question we're going to do first here.
Let's go gambling!
Oh, wow. Taco Man.
That's dope!
You had a 2% chance. You somehow won that. Congrats. Crazy. Install Linux. I use Arch. Okay. Okay, here we go. This was from Taco Man. Says, a simple pendulum near the surface of the Earth has a period of TE. The same pendulum is transported to the surface of the moon, where the acceleration due to gravity is apparently g over 6, and the pendulum has a period of TM. The ratio of TM to TE. Yeah, okay, great. So this is, let me remember how this thing works. I think it's omega for pendulums. Is equal to the square root of g over L. Do you guys know this? Is this given to you on any sort of like equation sheet? Maybe I can find, what is the AP Physics 1 equation sheet? Let me go find it one sec for you guys. Because these are good ones to know. The other one that's really important to know, like flashcard wise, this would be the square root of k over m. This is omega for a spring. It's on the sheet? Cool. Good. Yeah, so omega is square root of g over L. But then the key thing here is they're talking about period. So this is always what you guys should remember. So omega is equal to 2 pi f. This is the conversion between, this is called angular frequency. And like regular frequency. And then the other thing you learn is that f is equal to 1 over period. You're given t. Okay, great. If they give you t, then cool. I just know this because we use omega a lot more in upper division physics stuff. But great. Okay. So let's just say t for a pendulum. If they asked you for the frequency, it's good to know how to convert this. So t for a pendulum, I think is 2 pi square root of L over G, right? And then, yes, good. So, and then t for a spring must be equal to 2 pi square root of m over k. Yeah, so we'll get to it. I am Barry's like, it's B, it's B. Well, let's see why it's B, okay? So, we want Tm to Te. Okay, so Tm over Te is going to equal 2 pi square root of L over Gm over 2 pi square root L over GE. This is what I always like to just write this. I'll be like, okay, I need Tm over Te. Well, Tm is this, where I think also the L's are the same, right? A simple pendulum. It's the same pendulum. So if it's the same pendulum, same L. So now you just cancel stuff out. So this cancels with this. This will cancel with this. And so what you end up getting is... Here, I'll show a little bit of the algebra, because I know sometimes the algebra gets weird. This would technically be the square root of 1 over GM over the square root of 1 over GE. But then dividing fractions, easy as pie, flip the second and multiply. This is the same thing as the square root of 1 over GM times the square root of GE over 1. And so what you end up getting is the square root of GE over GM. And then they said that G of the moon is 1/6 G of the earth. So GM is equal to 1/6 GE. So then you can plug that into here. Yeah, so when finding ratios, you put both equation values and then over each other. Yeah, this is the number one way I do it. You can memorize like, oh, it goes a square root of this over this, and then you're like, okay, well, which one's... But it's fucking confusing, like which one's top, which one's bottom. So I just write them out. And then instantly I can be like, cool, cancel, cancel. And then flippy, multiply, whatever, get to this. And then you substitute in. So now I know that GM is 1/6 GE. So I'm going to write this as the square root of GE over 1/6 GE. Again, this is more algebra. GE is going to cancel. And then when you divide by 1/6, it's the same as multiplying by 6. So this is going to be equal to square root of 6. So that tells me that Tm over Te is equal to the square root of 6. Which, I think it's answer choice C then. Right? Tm... Yeah, should be this. So not answer choice B. I am Bury, unfortunately. I'm pretty sure it's answer choice C. And that should make sense because moon has less gravity, so stuff like kind of hangs and floats more. So that's why the period should be something bigger than 1, not less. Yeah. And then this, right, this is the same thing as square root of 6 to 1. Mistype? Okay, dude.
Disqualified.
Okay, there you go. Okay, nice, cool. So that's how that one works. Yeah, and if it was answer B, what would that answer? If it was B, what would that answer look like? So this would be the reason why they were trying to mess you up with this one. This would be if it was TE to TM. That's one. This would be, and that one's wrong. Yeah. She didn't know that fluids was on the unit.
Oh, brother.
Yeah, that's unfortunate. Okay, anyways. I'm going to save this question. This was Taco Man. So, all these questions I will put on our Discord. And so I'll show you like where those we have a Discord that we help out a lot of students in as well. And then we give out prizes and stuff for people doing well in school and life and things. So that all gets put in our Discord here under this channel homework help. So Taco Man, I'll paste the screenshot in here for you. And then the other cool thing is every time we do one of those questions, along with the answer, along with your question, there's also a link here to the live stream, and it's timestamped as well, so you can go figure out like where that happened. And then the link to our Discord is the same link that you guys are using to submit questions here. You just click on join our Discord. It's like right there. So go check it out. So the variable on the left is always on the top of the fraction. Yes, that has to do with that's how ratios work. Again, something that probably should have been taught earlier in school, but A to B is the same as A over B. Yeah. The best strategy to get a 5 if you know nothing, which is what, yeah. So this is also a ratio form. Then there's this form. Yeah, that's kind of mean they put it like this. Should have put it as a Sijihan equals Pex. Okay. The best strategy to get a 5 if you do nothing is if you know nothing. Oh, probably study and come back next year. For the ratio problem, can you set that equal to root 6 over 1 so you can visualize it better? You can set it. Yes, exactly. Yeah. I don't like how they wrote it like this. I would have said this, just root 6 over 1. Or just root 6. You choose C every time. Don't do that.
Oh,
Emotional, damn it!
Okay, let's go see the next question someone has. So I'm going to go to the queue here. We're going to go choose a winner and see who gets it.
Let's go gambling!
Damn, Albert, are you shadow banned, dude? You have the best chance every time. Albert, Okay, Blinding Storm got it this time. That's 15% chance. Let's see what you got for me, Blinding Storm. Ooh, we got stars and stuff. Okay. Do I have predictions for the FRQ? Ooh, good question. You know what I will do? When they release the FRQs, I will do a stream going through them and how I would solve them. Albert's like, where's my chance, dude? Don't worry, Albert. Yeah. Anything but fluids. There's definitely gonna be fluids. Okay. Sorry, someone said they want to, if you get to mine, show if it can be done with energy and not with force. Oh, interesting. Okay. Wait, what's the question asking? Sorry. Are they asking just what V is equal to? Like how were you saying? Because I think you want to do this one with force. So F is equal to MA. And in this case, the force that's pulling them in towards each other is always pointing towards the center of rotation. So this is the same thing as M times A centripetal. And then that's also equal to M V squared over R, right? So this object, as it moves, wants to just like keep going this way. Just wants to keep going that way. But there is a restoring force from this mass that's pulling it in a circular motion. Yeah. Let me show how to do it with forces, and then I'll try to do it with energy. But that's definitely not the way you want to do it. So this force, which you can call this like a centrifugal force, I guess, right? That's equal to G big M over R squared. So that's what this is equal to. And that's equal to mass times centripetal acceleration, which is mass times v squared over r. So now you can cancel. Great. One of those goes away. This is also equal to big M. So another one of the big M's goes away. That's cool. So then you're just left with v squared is equal to gm over r. Right? But r is equal to d over 2, right? Yeah, okay. R equals... Oh, interesting, actually. Ooh, there are two different R's. Ooh, this is tricky. This is tricky. This is tricky. Okay. You got to be really tricky about this. Sorry. These are different R's. Yeah, no, I'll show you. This is actually, yeah, it's because I hate this in physics. They'll use the same letter for two different things. Okay. With gravitational force, that R squared refers to this. This is what I would call like R squared. So this is really going to be D squared. Yeah. So, Charlie, good question. I just joined the Discord, so I'm sad I found you the day before exam. Yeah, no, good. Yeah, see me for, Physics C. We help everyone up to, like, differential equations in, like, college. Like, yeah, you're all good. Oh, you have to... Okay, so, let me see. So, gravitational attraction, usually, you will use this, F equals mg. That has to do with things on the surface of the Earth and objects that are just falling towards the ground. Simple shit. When you're dealing with stars and planets and satellites, like interstellar things, this is when you need to use F is equal to big G, and then it's m1, m2 over r squared, where r in this case, this is the distance between the objects. Good. How do you know if it's FC or FN or both? So in this case, normal force only acts if you have something it's resting against to provide that normal force. This is not normal force. This is a centripetal force, because this force keeps these objects moving around in a circle. All good. You know about me now. I say the best time to plant a tree was 40 years ago. The second best time is today. I guarantee you have more classes, so... So anyways, okay. So G, big M over D squared, that's the gravitational force between these two things. But that's equal to the mass times the acceleration of one of these objects, which is a big M, and centripetal acceleration is linear speed v squared over the radius of the circular motion. That one is now equal to D over 2. Okay. So, now when we go to solve this, this is cool. This is how this happens. This is going to go away. This will cancel with this. This will cancel with this. This will cancel with this. And now I'll get GM over D is equal to V squared is equal to 2V squared. Right? If I divide by a fraction, that comes up on top. And so then that's going to come underneath, and I'll get V is equal to the square root of GM over 2D, which, yes, that's answer choice B right there. Yeah. Cool. Yes. Why is R squared just D squared? I don't get it. Shouldn't it be D over 2 for the radius? Yeah, good. All right, so, yeah, key thing here. So, in terms of this equation here, for gravitational force, this R refers to the distance between the objects, and the distance between the objects is equal to D. Okay? So that's why that one is D. But in terms of rotational motion, so when something is going around in a circle, that R refers to, here, let me go with this. This is mv squared. We could say this is rc. That refers to the radius of the curvature, or the radius of the circular motion. So that's why that one is d over 2. So maybe let's like draw something here. Yeah, so this right here, this RC is equal to d over 2. And that's where this comes from. But this R refers to the distance between the two objects. Okay. I will say, just for me to like, you see chat just goes like crazy. I love it. I love the engagement. To make it easy, I will try to answer questions as they come in if they're related to what I'm working on. If you have a completely new question you want me to go over, the best way for me to like make sure I get individualized help to you and everyone else can watch it is take a screenshot of whatever that question is. Hopefully you have like an example question that's based on it. And if you submit it here to the website and just hit upload, it'll get put in the queue, and then we'll just randomly select which ones we go through. And if you wait, the ones that are in there for more time get picked easier. So yeah. So if you have something like, hey, could you derive this derive, just take a screenshot of whatever that text is, throw it in here, and then I'll show it. Yes, because the diameter is r over 2. No, diameter is equal to 2 times r. Yeah. Yeah. This, and technically, yes, this distance is a diameter, but yeah, that's equal to 2r. 2rc is what I would say. All right. Blinding Storm, I would love to see if I could do it with energy. It would probably take me a little bit more time. So just in the interest of me making sure I can help as many people as I can, I'm going to say that we did it this way. This is the way they want you to do it, by the way. But if you come by one of my other streams, like after the exam, I'm happy to try to work out how to do it with energy. I mean, I'm sure there's a way with Lagrangians and Hamiltonians, but that's like way outside the scope of this class. Tangent of theta is v squared over rg. I'd have to see that, Haster. Show me an example question of that, and I'll see it. It's hard for me to like sometimes see all the questions through text. Here we go. Let's pick another winner.
Let's go gambling!
Maybe Albert the Pirate gets picked. All right, we're getting closer. We're getting closer, Albert. We went to J this time. Okay. Yes, Theodore. Yeah, so real quick on this. So for centripetal motion, acceleration is v squared over the radius of the circular motion. Because this thing is going around in a circle this way, the radius of the circular motion is equal to this d divided by 2. But when calculating the gravitational force between the objects, that r that you use in this, that's equal to the full d thing. Yeah. And if you're still a little confused, so again, all the questions I put the solutions to, they get put here in the Discord. It's under like homework help. And then there's a link here to the live stream and when it happens. So you can go back and replay through it to try to see if it makes more sense. Okay, let me see this one. Okay, 2 blocks are connected by a compressed spring and are sliding together to on a surface with negligible friction. At some time t2, the spring expands and pushes the blocks apart. Sometime later, at time t3, the blocks are moving in opposite directions. Which of the following could be a graph of the velocity of the center of the mass of the block spring system if right is considered in the positive direction? I'm tempted to say it's just this. Because I think this goes back to what we did in the FRQ question, which is unless there's an external force on the system, that there can be no change in momentum. I want to say so. I want to say. What is the correct answer to this one? Is it you know, I use ChatGPT all the time. It's kind of fun to see, like, I want to see what chat says. I'm pretty sure it's A. Yeah, right, Lizzie? Yeah, center mass shouldn't change. Yeah, let's see. Yeah, cool. Okay, good. I'm correct. Yeah, flat horizontal line. Nice. Okay, cool. Yeah. This is a similar question that comes up when they talk about like the ice skaters that push off of each other. Right? They exert a force on each other, and then this ice skater is like moving this way, and then this ice skater is moving this way. But if you were to calculate the velocity of the center of mass refers to if I were to balance these two things, like where would it balance? That velocity still has to be 0. Yeah. So this came up a lot. Yeah. In terms of momentum FRQs pulse, that's what the first question was that we went over. That was this. Question 1. This was all momentum. And we talked about the same thing, right? If there's no external force on a system, then the momentum cannot change. So in this case, this is similar to the friction between the block and the car, keeping them together. The spring is an internal force. Because whatever force this spring acts upon the 5 kilogram object is going to be equal and opposite to the force that gets exerted on the 10 kilogram object from the 5. Yeah, so momentum is conserved. Yeah, so I would say this. It's like conservation momentum. Yeah, done by the system or on the system. Yeah. You don't do that as much in physics. That's more of like a chemistry thing when they talk about like the work being done by the gas or the work being done on the gas. I don't think it really matters as much in physics, the sign. I don't think we really, yeah. Okay, but this is conservation of momentum. And you can say like no external forces. You say spring is an internal force. So, V center mass is constant. You like my soundboard? Thank you. Okay, cool. Great. Done. Can you do a triple integral? Why would I do a triple? You don't need to do a triple integral. You don't have to do any integrals for AP Physics 1. Absolutely none. Okay, good job, Jay. Let me download that for you. Triple integrals? Yeah. Maybe if this was like upper division college physics, yeah, you could do a triple integral. You don't have to do it now. All right, let's go see what the queue's at. Here's the queue. I'm gonna go choose another winner. Who's it gonna be?
Let's go gambling!
Albert, come on, dude. Is it gonna be you, Albert? There it is, Albert. Good job, Albert. You got picked. Ooh, this is fun.
Aw, dang it.
This is gonna be a fun one. Do we believe? Are you doing a live for AP Calc? I wasn't planning on it. But again, I do these live streams 4 or 5 times a week. So if you ever go here to our streaming schedule, you can see all the times that we stream. So I do have a stream tomorrow, which is open. You can just ask whatever. It's not going to be specific to any class. And then we have another one on Thursday. And then, I don't know. I think AP exams are done by Friday, maybe. But yeah, feel free to check it out. It's a cool calendar. All right, let's see. A mass of 3m is attached by a string to a pulley. That string is attached to a mass of 5m. Another mass of m is not attached to the 3m block, and there's negligible friction. Find the acceleration of the system. Oh, this is cool. So, I think for all intents and purposes, this m is basically a part of this mass. If we really want to, talk about it, technically, for the force diagrams, this is going to have an F tension on it, right? And then it's also going to feel... Here, if we call this block 1, block 2, let's call this like block 3. It's also going to have F21 pushing back on it. But then this is going to have F12 pushing on it. Yes, normal force and gravity as well, but there's no friction in this, right? Yeah, no friction. When there's no friction, you don't really need to deal with, as like a little shortcut, when you have no friction, especially with these pulley questions, you do not need to deal with normal force or gravity, really. Well, I mean, you're going to have to deal with gravity here because the thing's pulling it down. But in this case, gravity and normal force cancel each other out, so I don't really care about it. But yeah, okay, so yeah, this one will technically feel F12 on it. So okay, let's keep all the forces. I'm cool doing it separately. I'm pretty sure this acts just as if it was together as 4M, but we can leave it. And then let's look at this. So the 5M is going to have force tension pulling it up, and then it's going to have in this case 5mg pulling it down, right? Cool. Now here's a key thing with these pulley questions. I always like to call a general coordinate system, which in this case I'm going to say it's something like this, where I'm going to say this is the positive direction and then this is the negative direction. So anything that moves in this direction for these blocks is the same thing as movement in this direction for this block. So when talking about directions here, this is plus, this is minus, and then when talking about directions here, this is plus, this is minus. We'll see. We'll see what we get. So yeah, let's do all the sum of the forces on everything. And then here's the key thing, is that because these things are connected by a rope, that means they all have the same acceleration. As long as the rope isn't like loose. If the rope is taut and tight and whatever, then yeah, they all move at the same acceleration. So, you got 5/9 times F. Let's see. So let's do it. Let's do the sum of the forces for this. So sum of the forces for block 1, you're going to have Ft pulling it in the positive direction to the right, and you're going to have minus F21 pulling it to the left, and that's going to equal to 3ma. And then for block 2, you're going to have just F12 pulling it to the right, and that's going to be equal to 1ma. Yeah. So here's kind of the cool thing here. Just right away off the bat, right? For this second block here, some students would be tempted to say that Ft acts on it.
Oh, no.
And that's not right. Ft only acts on block 3. It's the normal force from block 1 onto block 2 that causes block 2 to feel anything. Yeah. Good. Why is it only F12 and not F21? Good. So how I write things is I'm going to say that F12 is force of 1, or force of block 1 on 2. And then so that means F21 is equal to force of block 2 on 1, on block 1. It so happens in this situation that because these are force pairs, F21 is equal to F12. Like, they're equal in magnitude. You're getting scared for the derivations? Okay, well, submit a derivation question. I'll do it. You don't need to solve for triple integrals. Okay. So here's the key thing. Because they're a force pair, F12 equals F21. So you can take this and plug it into there and watch what happens. So this would get Ft minus ma is equal to 3ma. And so Ft is now equal to 4ma when you move this over. Notice that Ft is equal to 4ma would be the same thing if I considered this whole system as a single block, which had mass 4m, and just had Ft pulling on it. You see how that's the same thing? Okay. Cool. All right. So that's for those. Cool. So we got this for the first part. But then let's do something with here. So in this block, I have the force of gravity pulling down. So let's do the sum of the forces on the third block. So that's going to be positive 5 mg. Why is F1 equal to F2 Because they're called I think it's Newton's third law, but for every force, there's an equal and opposite force. So because this block pushes on block M, this block is going to push back with the same force. And where do I get the 2ma? Not 2ma. There's not 2ma. The 3ma, yeah. The 3ma comes from when we're looking at the first block here on the sum of the forces. So you have Ft minus F21 is equal to ma. The m is 3m. And then the acceleration is a. Is Newton's third law? Okay, great, yeah. So that's where that comes from. And then what I did was just to show you, the shortcut is just like absorb this into this and call it 4m and you're great. But you could also individually look at the forces on this little block, which I'm calling block 2. And the only force acting on that block is the force from the first block acting on the second block, F12, which is equal to ma. But I say, oh, but F12 is the same thing as F21. So instead of writing Ft minus F21, I can write this as Ft minus ma. And then when I move that over, that gets me that Ft is equal to 4ma. Yeah, okay. But isn't the force on block 3m 5 mg? Not quite. Not quite. I'm going to show you. Okay, because look, for looking at, this is why you have to write out the sum of the forces for all the individual blocks and then look at the math. I know it seems like that Ft should equal to 5 mg. It doesn't. Because depending on how heavy stuff is here, the tension in the rope will change. If this was massless, then yes, whatever was here would feel the full 5 mg. But because there is weight here, that's going to create tension in the rope, which is going to slow this down from completely falling, just free fall. Yeah, you guys got it. Okay. So look, for the sum of the forces on F3, you have 5 mg minus Ft, and this has to equal 5 ma. Exactly. Yeah, no, if Ft was greater than 5 mg, then we'd have big problems. Then the block would be falling up. Okay. So this came from here. Here, I'll draw some colors for you guys. Colors are great. We love colors, right? This came from here. This came from here. And then this is like the combination of the two. All right. So now I have two equations, and I have two things I don't know. I don't know the acceleration, and I don't know Ft. I technically don't know m as well, but whatever. They want us to find the acceleration. So in this case, I'm going to do what's called the elimination method, or really just substitution here. And I'm going to substitute 4ma in here for Ft. Okay? So now I can say, okay, cool. 5 mg minus 4ma is equal to 5 ma. So then move that over. And you get 5 mg is equal to 9 ma. Cancel the m's. And you get a is equal to 5/9 times g. And that's going to be accelerating downwards. So notice that this thing is not accelerating at g. It's accelerating at a fraction of g. So this thing does not fall down in total, free fall. Yeah, flipping physics. Yeah, he's great. I know Jonathan. He's a cool guy. He also has a lot of great videos. Yeah, I'll plug his channel all day. If you guys don't know flipping physics, I'll go show him. He does that full time. I run a nonprofit and I teach at UCLA, so I do a lot of things. But flipping physics is great. Yes, I highly recommend. He's got a lot. They're like more long form videos if you're cool like sitting down. But okay, little bit of warning here though. I'm a very big advocate for active learning. Like you have to do shit to learn shit. You can't just sit in front of videos and just hit play and just hope like by osmosis that you just get hypnotized into knowing it. That doesn't work. You have to do the problems. So I tell people the number one way to get good at physics, the number one way to do well in exams is to do problems. So if you have practice stuff, please go do that. We also have practice stuff on that Kudu class. I think that should have gotten linked to you guys. Where did I have it under? 1 sec. It's under our website. Yeah, here under AP Physics 1. This also has hundreds of like practice questions that you can go do. So you can go click and like sign up for them. I'll drop the link here for this as well. So yes, while I do think I love Jonathan, I think he has great videos. Make sure you still actually like do questions though, rather than just reading stuff. You got to do stuff. So there's the link there if you want the extra practice questions. We also do some like cool fun short form videos if you want to check out our channel. We got if you ever go to the playlists here under, I think it's like, yeah, physics in 60 seconds.
How to solve a 1D project.
We have a bunch of fun little videos on how to do, this is for instance like how to do conservation of energy.
In later potential,
We put like a bunch of fun memes in it. But usually what I'll always do in one of these videos is I will do a question and I will walk through how to do that question. And I think that's the best way to teach. So yeah, so go check that out as well. The links for all that again are on the same website you guys are using to submit questions. You can go visit our YouTube there, and then they're on that channel. I wouldn't skip. I mean, yeah, it is the day before the exam. I would try to do some core questions for oscillations, just so you kind of understand it a little bit. Yeah. Okay. Let me see. So, good. We got 5/9 G. I think this is great. I'm gonna mark this question as done. Good job. Thank you, Albert. I hope that makes sense. And here, I will add more time on our stream today because it says we only have 18 minutes left, but I'll give you guys some more time. You guys. All right, let's see. Cutting into my workout time. It's okay. Okay. Cool. Let me download this one for you, Albert. Please go over fluids. The best way for me to go over fluids is if people can drop me screenshots of fluid questions. The problem with fluids is a very big topic. So for me to like just go over fluids would be a lot of things. And I don't know like how in depth you actually have to know fluids. So someone drop me a screenshot of a fluids question that is from a practice thing or whatever, something your teacher gave you. I'll do it. And then I'll explain the concepts behind it. But okay, cool. There are some questions. Let's go spin for a winner. And I'll go do it.
Let's go gambling.
Quillen.
Emotional, damn it!
That's not a question, Quillen. Okay, please actually post questions. Don't post rage bait and shit, please. All right, let's do it again. There we go.
Let's go gambling.
How is it for you having external knowledge and needing to explain it in basic AP Physics level? It's fun. I enjoy it. There we go. Great. Okay, cool. Yeah, this is a great question. I do like this one. I know which one this one's asking about. Okay. Yes, is how do you derive tangent theta is equal to v squared over rg? Yeah, great. That's totally valid. Yeah, okay. Okay. So this is kind of centripetal. Yeah, this is circular motion. You got this. Okay. And then this is going around in a circle. Something like that. Cool. Okay, and then you're saying this has a length L, and then this is at an angle theta. And okay, I get it. And you want to know how fast this needs to spin in order for it to have this angle, right? This is like if you're spinning like a lasso or something, right? Okay. So, let's consider what the forces would be at this point, all right? So you would have mg pulling down. Let's just assume you have some sort of mass, right? Mg is going to be a force pulling down. You're going to have Ft, or here, let me draw this somewhere separate, because otherwise there's too many arrows. Let's do this, okay. You have mg pulling down. You're going to have Ft pulling up. And if this right here is theta, this is where sine theta and cosine theta actually flip, because you're using a different theta. Okay. If this is theta, then this is going to be Ft sine theta, and then this is going to be Ft cosine theta. Right? And then, the reason for that, right? Cosine, this is the adjacent to this angle. This is the opposite. Usually y direction stuff is sine, but in this case, it's cosine. And then we know that the acceleration, which isn't a force, I'd like to just draw it as an arrow. The acceleration here is going to be equal to v squared over r. Okay. And okay, so in order for this thing to be staying upright, I need this force to equal this force, right? So my up-down force have to all cancel to 0. So I'm going to say sum of forces in the y direction must equal 0, because there's got to be no acceleration up and down. And that means that Ft cosine theta must be minus mg has to be equal to 0. So that tells me that Ft cosine theta is equal to mg. Okay, great. Then let's look at centripetal acceleration, okay, which is in the x direction, and let's look at the forces in the x direction. So some of the forces in the x direction, which is just going to be Ft sine theta, that needs to equal to mass times acceleration, but the acceleration is centripetal, so that's going to be m v squared over r. The reason why it's centripetal is if we were to look, let's say, like top down, okay, you have this thing moving around this way, right, which is going to have a centripetal acceleration pointing inwards. And so if I start looking at this from like the side view, which is what we're doing here, we're kind of looking for the side, now that centripetal acceleration points in this way. And it looks like a left-right force on the block. Okay. Milla, if you want to help with that question, take a screenshot of it. Drop it in the website here. Just drop it in. We'll get to it. Okay. So, that's why this is equal to this. So now I can say, cool, Ft sine theta is equal to m v squared over r. And, sorry, what do they want? They want something with tangent? I think I know where this is going to come from. Okay. Ft sine theta is equal to this. Ft cosine theta is equal to this. This is kind of a cute thing you can do in math. I can take equation 1, and I can divide it by equation 2. Let's divide the 2. So now, this is going to give me Ft sine theta over Ft cosine theta. And then that's going to be equal to mv squared over r over mg. So Ft cancels. Sine theta over cosine theta is tangent of theta. So this is another thing that's important to remember. Yeah, you can totally do that. Yeah, as long as you divide everything. So as long as you divide the left side by the left side and the right side by the right side. It's the same thing in, you guys do it for the elimination method when you do this stuff, like x plus 3y is equal to 6, and I don't know, like, 2 minus, or 2x minus 3y, right, is equal to 4. Remember how you guys just add these, and then this cancels, and you get 3x is equal to 10 or something, right? That's another way to do it. So you can add equations to each other, and you can also divide them. So I'm just dividing this by this. So this over this, the ft cancels, and then sine over cosine is tangent, and then so now the m's cancel, and so now I get v squared over r, and then divided by g is v squared over rg. So that's where that comes from. I think the question was asking, how do we just get to this? You tell me, it's Haster, if that's cool. I think he was just asking conceptually, how do I get to that? Yes, you can also do that as well. Yeah, easy peasy. Yeah, you could do that as well. That's another way, Shahir, for sure, is I could have just taken this and said that ft is equal to... well, no, actually, I want to take this one. I would say that ft is equal to mg over cosine theta, and then you could have just plugged that into there. That's another way to do it. That was it? Cool. Awesome. Great. Yeah. Yeah, 2 ways to do it. How do you know when you should divide equations? Good question. Yeah. All right. So my intuition, anytime you have just simple this equals this, this equals this, and you see like some unknown variable you want to cancel out, and if you just divided them, it would go out. That's a great time to divide. It's, again, you could do substitution. Shahir was right. It's just this is faster. In the same way that if you had like x plus 3y is equal to 4 and 2x minus 3y is equal to 6. Yes. Could I solve for x? I could solve for x, right? I could say, okay, cool. X is equal to 4 minus 3y. And then I could plug it back in and then I could solve, but it's just messy. It's a lot easier in this case to add these two equations because I instantly get rid of that variable.
You're not that guy, pal. Trust me. You're not that guy.
And then I would just get like 3x is equal to 10. So mainly when you're solving systems of equations, when you have two things that are unknown, if you see that adding them would get rid of them, then cool. If you see where dividing them would get rid of them, then just divide them. The only case where I wouldn't use this is if you have this like plus like other stuff. Because, or, you know, if there's additional like plus stuff happening. Because then you can't easily like cancel things as nicely. Yeah. Yeah. If you have like A is equal to B and then like, I don't know, like 5A is equal to like B plus 2. It's a lot easier to just like divide these two. In this case, I would do 5A equals B plus 2, and then I would divide by A is equal to B. And then you're good. And then you just have, oh, cool. 5 is equal to B plus 2 over B. That's another way to like cancel things. Or you could just substitute it in. This is kind of a bad example, but yeah. What's the noise in the background? There's some soundboard stuff. Yeah, you divide to get rid of. I think the other case this could have happened, let me think. It does happen a lot here sometimes. If you wanted to like get rid of acceleration, you could have done this divided by this. Like if you wanted to solve for tension off the bat, you could have done this equation divided by this equation, and then the MAs would all have canceled. And you would have gotten 5mg minus ft over ft is equal to 5 over 4. Yeah. It's been stuck for so long. Well, yeah, okay, cool. All right, one sec. I will get to them, don't worry. Cool. All right, good. Good question. Let me add that in there. I'm trying to get that #1 rank aura. Good for you, Ironbury. All right, that was Haster. Let's mark that as done. And then let's put that in there. Cool. Everything I do gets put in the Discord here, so go join the Discord if you want to go see the questions. And we do a lot of fun stuff. We like have chess tournaments and shit. It's fun. All right, let's go to the queue. Queue's getting big. Love it. I also cap the queue. You can't submit more than 2 questions at once. And if you want your question to get selected more, hit the upvote button. You can do that every 3 minutes. There's a lot of gamification to this. Let's go choose a winner.
Let's go gambling!
There you go, Lawson. Okay, Lawson. Good. Cool. Ooh, this is work. Love this. Okay, there we go. Okay, a block is pushed up an incline with a rough surface at a constant speed v. Okay, constant speed. You should know this automatically. A equals 0 from this. With a constant force L, the coefficient of friction is mu k. Which of the following correctly describes the work done by gravitational force and the work done by the normal force on the system consisting of only the block as the block moves? Okay, great. Oh, man. Okay, on the system. Positive work. Okay, positive work is when force and distance are in the same direction. I don't think you're ever going to do work being done by the system. Systems don't really do work. I mean, you do work on the system, but yeah. Okay. So positive work is when force and distance are in the same direction. Negative work is when force and distance are in opposite directions. And if you want to know where that comes from, that's from this. So work is equal to F dot D, which is the same thing as FD sine theta. This is the angle in between the forces. And so if theta is equal to 180 degrees, then sine theta is equal to -1. Or, wait. No, it's FD cosine theta. I got that wrong. There you go. Sorry, my bad. There you go. Cosine theta. I was thinking about torque we did earlier. That one's sine theta. This is equal to -1. Okay, let me see what Shahir says. Yeah, okay. So when they're in opposite directions, you end up getting negative work. You can also think about, like, you know, positive work is when the effort you're putting into something is going in the direction you're putting the effort in, right? If I'm trying to, like, push something and it's moving in the direction I push it, I'm doing positive work. If I'm trying to push something and it's moving the opposite direction, that's negative work. Like, okay. Work done by the normal force on the system. So normal force is pointing up, and the object is moving up. So I'm tempted to say that the work done by the normal force should be, I think, work done by the normal force on the system. Shouldn't that be positive? Wait, this is kind of weird. One sec. Oh, wait. Let me think. Oh, it is negative. Oh, this is so weird. Ha!
Oh, brother, this guy stinks!
Man, they had to do that to us? Okay. Yeah, okay. Normal force is pointing this way, right? This is Fn. Which way is the distance pointing? Distance is pointing in this direction, right? This is the distance. In this case, the normal force is pointing in 0 direction of the distance. So the work done by the normal force is 0. Yeah, it's 0. Thank you, Jorgen. Yeah. That also has to do with this. So if theta is equal to 90 degrees, then cosine of theta is equal to 0, and that's 0 work. Thank you, Shahir. Normal is 0. Normal is 0. Gravity is negative. Yes, because gravity is going to point down, and technically, in terms of the distance that's happening, some of that distance is happening in the up-down direction. So this is where you have to, like, break down components. So technically, the up-down component of distance is up, but the up-down component of gravity is down. So these are opposite directions. So, yeah, work done by gravity should be negative. So the answer should be answer choice A, I think. Yeah. Answer choice A? I think so. I think it'd be A too. Yeah. This is where you guys are in AP Physics 1, so you haven't really done dot products really per se. But this is the same thing as we say like F parallel to D or F times D parallel. So I would say like the amount of F in the same direction as D. And then technically it's a dx and it's an integral, but and then this is the amount of D in the same direction as F. They make it seem hard, Jackson. I mean, I won't sugarcoat it. Like, it is a difficult exam, but it's not impossible. Yeah, it's not one of these where you just you can go over it. Can you go over deriving the expression? I think it just comes from this though. Kareen, I think it's just because work is technically equal to this. But this is the scary calculus one, which I don't think you need to know this for AP Physics 1. Yeah, okay. I got you, Milla. Okay. So let's think. Okay. Work. Positive work is when the force and the distance that something moves are in the same direction. Okay. Negative work is when the force and the distance it moves are in opposite directions. And then zero work is when the force points, we'd say like perpendicular to the direction. There better not be fluid experimental questions. That'd be super mean. You're not gonna fail. You guys got it. Okay, so Millie, let's look at this, right? So the direction this thing moves is this way, right? When the thing moves up and down the ramp, right? The normal force always points normal, which is 90 degrees, to the surface. So because these two have a 90-degree angle to each other, there is zero work. None of this force points in the same direction as the distance. So that's why zero work is being done by the normal force. Okay? If we're looking at the amount of work done by the amount of work done by gravity, okay? Well, gravity doesn't point normal to the surface. Gravity points straight down. Okay? So straight up and down is gravity. Okay? So let's look at the distance. Does the distance move in the up and down direction at all? Turns out it does. The distance is diagonal, which means it has some component going up and it has some component going to the left. We only care about the component that's in the same axes or the same type of direction as the force. Gravity is an up-down force, and because it's down, it's negative. The distance has an up-down component, which is up, so it's positive. So because this is opposite to this, that means there is negative work being done. Am I doing a Calc BC review before next Monday? Not formally, but you can ask Calc BC questions throughout the week on my live streams. You totally can. You can come by and ask them. Yeah. Does that make sense, Millie? A little bit more? Yes, it's because of the X and the Y components, Millie. Yeah, exactly. The distance has X and Y components, and so the Y component of distance is in the opposite direction as the Y component of gravity. The normal force has no components in the same direction as distance because it points 90 degrees to it. Yeah, cool. Okay, good question. We'll move on to the next one. If you guys want help with fluids, go find me a fluids example. I'll do them. Lawson. Okay, cool. Lawson, there's your question in our Discord. So there's the screenshot of everything. So you guys don't have to like write everything down. You can go download them later. All right, let's go see what's on the queue. Queue keeps getting bigger. Let's go choose a winner. Who's gonna be?
Let's go gambling!
I'm not... I can help out with AP Physics too, but I'm not going to do a dedicated review for it. Nitin! There you go. Okay. Ooh, this is fun. But again, yeah, I teach everything. Anything math or science from middle school up through like early college, I do help out with. So if you want help with any of that, go check out on our website. There's a streaming schedule here, and this will have all the different times and dates that we stream. We're Actual Education, but we have other friends that do math. So Zach, E2iPie, is another great guy. He does math streams if you want to ever get help with math. And he does like advanced math. He can go all the way up to set theory and stuff. He's crazy. Parallel axis theorem, please. Okay. All right. Let's see. A disk of mass m slides across the floor at a constant speed v. The disk collides with the wall at an angle theta and bounces off the wall with the same angle theta with speed v as shown. What is the magnitude of the impulse? Great. Okay. So we did this, right? Impulse is equal to F delta t, which is also equal to m delta v. If you forget this, always remember F equals ma. Acceleration is the same thing as change in velocity over change in time. So then you can like move this over and you just get that F delta t is equal to m delta v. And then these are all equal to impulse. Cool. What is a derivation? Derivation is where like you come up with equations from other equations. Okay, so let's think about like what's changing in terms of the velocity, okay? So the velocity is going this direction, and it's going to have some components, right? We anytime you deal with impulse or momentum or any of this stuff, you got to break it into components, okay? So here, it's going to have, this is going to be v cosine theta, and then this is going to be, I'm going to say like negative v sine theta, okay? Because it goes down and then it goes to the right. Then look what happens when it bounces off. Again, you have v cosine theta to the right. But now you're going to have v sine theta pointing up. Let's make that a little cleaner, sorry. Okay. So let's look at what happened, right? So impulse is the same thing as mass times change in velocity. What was the change in the velocity? Well, in the x direction, the change of the velocity in the x direction, that's equal to 0. Because it was going v cosine theta at the beginning, and it's still going v cosine theta at the end. In the y direction, however, delta vy, that's the same thing as v final minus v initial. So that's going to end up being, what was my final velocity? My final velocity was positive v sine theta. My initial velocity, exactly, you got it, Shahir, was equal to minus negative v sine theta. So minus minus is a plus. And now you get 2v sine theta. And so this is the change of the velocity in the y direction. So then impulse is equal to m delta v. And so that's going to be 2mv sine theta, which is, yeah, this answer choice. Answer choice C. There you go. May the 5th be will you? Yeah, Millie, so yeah, you're right. Usually y direction things Yeah, it has to do with the direction of stuff, right? This one was v cosine theta in the x direction. Right? The x direction didn't change. It goes from going this way to still going this way. This, it goes from going down to going up. So the change in it is twice that, right? Because it has to go from this to stopping to going up. So it's twice it. Nice. Okay, cool. You got it. Nice. Answer choice B. Did that make sense to you, Nitin Garish? Nitin? It's a cool name. Yes, because of the change in B. Exactly. All right. Nice. Let's go spin some more wheels. See what we got. And here we go. Let's go gambling.
Let's go gambling!
You're welcome, Nitin. Glad. Calc is fun. Now, I will say, if this is a calculus question, I won't do it because I want to help you with physics. Okay, but this is great. Okay, this is yeah, great. This is whatever thing, fluids. Okay, I can do this. It's okay. Let's do it. You're going to the exam in 2 hours. Godspeed. Good luck. Okay, let's see. Okay. Here we go. 3 small cubes, A, B, and C, are released from rest at the bottom of a tank of a density rho naught. The 3 cubes have the same volume, and the densities of them are different, where A is more dense than B, more dense than C, and is more dense than rho naught. The forces exerted on A, B, and C by the bottom of the tanks are FA, FB, and FC, respectively. Indicate which of the 3 forces is the greatest. Okay. Fascinating. They're at the bottom of the tank. This is always the issue. There's no fluid at the bottom for this, right? Oh, you're in the wrong class. Oh, it's okay, Lucky Cat. Okay, you're good. Here, I'm gonna delete 3. Okay. What I want to say is, in terms of force of gravity, right? Because they have the same volume. So force of gravity pulling down is always going to be equal to rho v naught times g. And then the buoyant force is going to be equal to that's going to be rho of the liquid, and then that's going to be times the volume it displaces times g as well. Okay, great. Okay, cool. So let's look at the sum of the forces on the object, and they're released from rest, I guess, right? Okay, so you're going to have Fg, which is going to equal to rho v naught g. And then you're going to have the buoyant force, which is going to be equal to rho of the liquid v naught g. And then here's the key thing here. They say that the densities of the cubes are more than the density of the liquid. So that means all these are going to sink, right? They're not going to go up to the top. So they're actually going to... So for here, force of gravity is actually going to be bigger than the buoyant force. But we need to make sure that these cubes don't, like, sink all the way down to China. So there has to be an additional normal force pushing up that's keeping things at least at equilibrium. So the sum of the forces either has to be 0 or it can be positive. These things can't accelerate any further down. They can't accelerate further down into the ground. So there does have to be a normal force. Okay, so here's where I'm going to get. So because force of gravity is greater than force buoyancy, all sink, right? So Fn plus rho naught v naught g must be equal to rho of whatever the thing is, v naught g. Okay, so then here's the key thing. If this is greater, then this must be greater. So here, this is like rho of the the number or the letter. It's Archimedes, yeah, not Bernoulli's. Yeah, this is Archimedes. Does that make sense, Milla? So far? Again, things that are denser than the liquid they're in will always sink. Just from this, because the buoyant force depends on the density of the liquid. The gravitational force depends on the buoyancy of the thing. And so if the thing is heavier or denser than water, then it sinks. Okay, why is FG greater than FB? Because they tell us that the densities of the cubes is greater than the density of the liquid. Yeah, because it's sinking. Yeah, but the good question is like, why is it sinking? It's sinking because the force of gravity is this. And then we can say that rho whatever number is always greater than rho naught. In this case. It's not always the case. Okay. This is density of the liquid. This is the density of the cube. Okay? Does that make sense so far? I don't know what problem set this is. This was just given to me. Someone gave it to me. Someone else can talk about it. Okay. So, because they're all sinking, we need Fn. No. To keep them from sinking in the mud. Them stationary. From falling below the ground. Use the density formula for each cube, and since the cubes have the same volume, the masses are different. Yeah, that's one way to do it. Yeah, I mean, FG is also equal to... So this density times volume is also the same thing as mass times gravity. But I think that's harder to see, Shahir, about this enforcing that they're sinking. I think it's easier to see it just in terms of rho v naught, rho v naught, rho v naught. So this is what you have. Because the force of gravity pulling these things down is more than the buoyant force pulling them up, you need an additional normal force from the ground to keep these things from falling like below the ground. So by sum of forces, we need these to equal this. Yeah. The densities are proportional to F. So, yeah, we're going to get to that. So, they're proportional to Fn. So, yeah, by this, right? Here, these are the up forces. I'll call these up. I'll call this the down force. If the density is higher, then the normal force must be higher. This is constant, because this is from the liquid. So FA is the greatest, correct? Yes. This one's the greatest. Justify qualitatively, I would just say has the most FG, and I would say all have the same buoyant force since they all have the same volume. Because buoyant force only cares about the density of the liquid times the volume that's being displaced times G. This is density of liquid. This is the volume of liquid being displaced by an object. And then this is the gravity. Is that not referencing equations? Beyond referencing equations. Yeah, okay. I mean, I would say they all have the same FG, all have the same buoyant force, they all have the same volume. So normal force keeps it from sinking below the ground. Yeah. They all have the same volume, and yeah, buoyant force doesn't depend on the density of the object. That's what I would say. Then they say, okay, go do an equation for it, right? Okay. And then they just want to find the equation. The equation's this. So now you just go from here. We already derived it. This is what you would say. You would say this minus this. So sum of forces is that, and that has to be equal to 0. And then I think they wanted to call this P1. So you could say Fn is equal to rho 1 minus rho 0. And then that's V naught G. And so from this, you can see that the more dense your object is, the more the normal force is. Yeah. Yes. Yes, I agree, Shahir. That's another great way to put it. Yeah. Here, I'll rather than me like write that all out again, I'm just gonna copy paste that in for you. This is also correct. I agree with this as well. Yes. Cool. I'm so cooked. No, dude, you're not cooked. It's okay, dude. Don't worry. Okay, there we go. I think this is good. We'll save this. Take a look at it. It's a pretty fun question. They've all been buoyancy. Where's the fluid equations on like Bernoulli's? I haven't had any Bernoulli's questions yet.
Well done.
Okay, and this was Calc is fun. Calc is fun. Calc is fun. Who is we? We is y'all. If you're in this stream, you're already doing better than probably most people who, I don't know, are not studying. Or doom scrolling through feet pics or something, I don't know.
Oh no.
Great, yeah, you're welcome, CalcFun. It's in the Discord there if you want it. So if you guys want any of the solutions, I'm posting all the screenshots there in the Discord as well. So you can go check them out. You canoed to Bernoulli's one? Nice. Okay, let's go check it. What do I need to make sure the FRQ is regular P1 equals P2 to make sure I get those extra points for saying they're equal to each other? P1 equals P2. What? We didn't have any P1s equal P2 here. My class gave up? Oh no. Never give up. Okay, here we go. 23 questions. Wow, okay. Let's go find a winner.
Let's go gambling!
I don't think I've ever seen this many questions in the queue. It's kind of fun. Who's gonna get it? Oh, there you go. Heimbury. What'd you give me? Okay, cool. Your class has been playing Brawl Stars? Oh no, dude.
No, God!
That's not a way to study for the exam. Alright, a spacecraft of mass 3m and an object of mass m. Alright, let me label some stuff real quick. Oh, they label it for us here. Okay, whatever. Are connected by a cable. The spacecraft pulls the cable, bringing the spacecraft and the object closer together. The spacecraft and the object are in deep space, far away from any other massive objects, and the rocket engines are turned off. If the large dot in Figure 2, which point on Figure 2 best represents the location where the object will meet the spacecraft. I think it's gonna be the center of mass, right? Yeah, I think it'll be the center of mass. Just because, think about this. These two things, they're pulling on each other. This is similar to some other questions we did. Which one was it? Was it this? Yeah, this one, right? With the ice skaters pushing off on each other. This is like the opposite. They're like coming together. And then also with the spring and the two masses. If there's no external forces acting on the object, then the momentum has to stay the same. So if these things are at rest, you can say that P total is equal to 0. So the velocity of the center of mass has to also be equal to 0. So once this starts pulling on this, that's an internal force. Like, there's no external force on the system. They're pulling on each other. So you need, again, when they're close to each other, that center of mass is still always going to be have 0 velocity. So yeah, I think we do it this way. Oh, they don't even have like numbers for shit. They just want you to figure it out. Oh, okay. Well, I assume this is like halfway. I think you could actually figure it out, right? Does anyone remember what the center of mass equation is? So it's sum of mass times position over sum of masses. Yes, total momentum is conserved. They'll have to meet at the center of mass, right? Yeah. Yeah. Just use the equation sheet. I mean, I kind of like to just know stuff. This is the center of mass equation I know about. So this would, if I call this like x is equal to 0, so that would be 3 times 0 plus, I don't know, let's call this, I'm going to call these quarters, so I'm going to call this 1. Or actually, let's call this 4. I'm going to say plus 1 times 4. And then this is going to be over, or sorry, this would be 3m times 0, sorry, times 1m times 4. And then the sum of the masses would be 3m plus 1m. So you would end up getting 4m over 4m, which is just equal to 1. And if this distance is 4, then 1 should be here. So it should be just answer choice B. Give me equations like this and I was flying high, yeah. Yes. The objects experience the same attracting force. That's another key thing. Yeah. So another thing with tension in a cable is that Ft is the same on either end. And since Ft is equal to Ma, if you have a higher mass, then you have a slower acceleration. And vice versa. If you have a lower mass, you have a higher acceleration. So this object will accelerate more than this one will. And so you would expect this one to travel further than this one would as well. This one would as well. So yeah, that works as well. I've said as well 4 times today. Okay, great.
Emotional damage.
I think it's done. Okay, cool. That was Lambury. Question, Lambury. You never seen that one? That's kind of a cool one. Yeah, center mass is hella useful too. Okay, so that was Lambury. Mark is done. Put it in our Discord. Where is it? There you go. Oh, it is? It's on the 4th of the reference table? Yeah. Yeah, there's a couple ways to do that one. Okay. Let's go see what's next on the queue. She keeps getting bigger and bigger. Wow, 27 questions. Y'all gonna break my queue. I vibe coded this whole thing on ChatGPT. All right, let's go choose a winner.
Let's go gambling!
Jay with the fluids. Oh, here we go. Yeah, that's a good one. Here we go. Fluids. Q is cooked. And that's why I make it random, because honestly, if it was first come first serve, no one would submit questions because they're like, there's no fucking way I'm getting picked. Right? Because it's so many. You'd be like, there's no way he's getting to me. But we incentivize people to stay active, because if you keep hitting upvote, you keep boosting. All right, here we go. Sphere A, mass M is released, and radius R is released from the bottom of a large pool of water. Sphere A is released at t equals 0, rises to the surface, and at time t equals 1, it is just below the surface of water. The density of sphere A is less than the density of water. That's good, because otherwise it would sink. Resistive forces are negligible. On the dot, represent, draw and label the forces that are exerted on the sphere just after it is released from rest. Each force must be acted. Okay, cool. Cool. Okay. Well, we did this a little bit earlier, but let's remember. So all objects on the face of the Earth here have a force of gravity, which is equal to mg. And what we learn for mass, right? So mass is also equal to density times volume. Did they give me m? Oh, they did give me m, so I actually don't need it. Okay, great. But another way to write this is, you could say that this is also equal to the density, which would be, what's that going to be? M over... Well, actually, I don't know the density of it. Do I know, right? The density of sphere A. So they didn't even give us a number for this, man. It's kind of whack. Let's just call this rho A. Let's call that rho A. So this is the same thing as rho A times pi 4/3 pi r cubed, if you really want it, right? I'm gonna leave things as symbols. I'm gonna say rho A VA times G. Okay, let's just leave that like that. All right. Then there's going to be a buoyant force, which is going to pull this thing upwards. And then because we know it's accelerating towards the top, we know that that force has to be greater, because I need the net acceleration to be positive, right? I need the sum of the forces to be positive. So sum of the forces, which is equal to F buoyancy minus F gravity, that has to be positive for upwards acceleration. Cool. So, that force, buoyant force, is going to be equal to rho of the liquid. So we're going to call that rho of the water, rho W. And then it's times the the volume of water that's being displaced, which is the same as the volume of the sphere. And then that's also times G. And then I think if they wanted you to really like put stuff in there, you could also say that VA is equal to 4/3 pi r cubed. And then I guess you could say that rho A is also equal to m over 4/3 pi r cubed. That's just kind of messy to have to do all that. All right, yeah, getting the basics down. You're good, Liam. How do you write so small with a mouse? I have a tablet thing. It's the only way I could do it. Okay. So I think that's all you have to do is draw and label the forces, and then they just want the relative lengths. So you actually didn't even have to do this, but it's just good practice to know that the buoyant force is always the density of the liquid it's in times the volume it's displacing times gravity. Whereas the gravitational force is always the mass of the object, which is usually the density of the object times VA, the volume of the object times gravity. Yeah. So there you go. That one's not too bad. Yeah. Oh, thank you, Vix. You're good. Appreciate the donation. All right, cool. Yeah, good. Good question. Don't be scared. Yeah, don't worry. We're there's safety in numbers. Whose was this? This was Jay. Someone go find me a Bernoulli question. I know you said you found one for me, Lawson. So we'll see where it comes up. Could you explain the volume displaced and the force buoyancy? Yeah, sure. I totally can. Yeah, so let me show it real quick. I can probably get a picture of it. One sec. Let me just get a picture of it, so I'm not drawing so much shit all the time. It's called like Archimedes principle. Someone got a nice picture? Come on, dude. Man, this is the lowest. What is this? McDonald's Wi-Fi resolution, dude. Something nicer. Oh man, come on, guys. No one does this. Okay, this is actually kind of a fun diagram. Yeah, I know this one. I've seen this one. This person doesn't look like they're swimming very well. Yeah, okay. So, if you are swimming, and hopefully not swimming badly like this person, you have a couple forces on you. You have the weight of you, which is also called the force of gravity, and then you have the buoyant force that tries to like push you up, okay? The way we figure out what the buoyant force is we pretend that you were invisible, okay? Like you were, I just draw something else, don't worry about that. We pretend that you are invisible, and we calculate what is the weight of the fluid that you are displacing, that you are pushing out of the way. It turns out that the weight of that is equal to the force of the water pushing up on you. The secret to underwater propulsion is dislocation of the shoulder. So, yes, buoyant force is equal to the density of the liquid, which we say is like FL, and then it's the volume you're displacing times gravity. What is the background? I don't know. I think this is supposed to be an outline of what you are, but it kind of looks like Donnie Darko, like the scary rabbit or something. Yeah, that's the best I could come up with a diagram for it. So yeah, the fun example we did earlier to show, I think we did this with, was it with you, Milla? Actually, maybe it was with you, Milla. Was this case when, let's say for instance, you have a cube that isn't fully submerged, okay? So let's say you had a cube like this where only part of it was submerged, okay? So it turns out that the force of gravity that's pulling you down is equal to the whole mass of the object times the gravity that's pulling you down. So we would say the mass of the object there would be the full density of the object times, in this case we said it was a cube of length L, and then times G. So this is the force of gravity. Force of gravity is always density times volume times, well, the mass is density times volume, and then it's mass times gravity. So mass is density times volume times gravity. There you go. That's the force of gravity pulling this thing down. However, some of this cube is displacing, it's pushing out of the way some of the water. Not all of the cube is pushing away the water. Only this part of it is. So the buoyant force is equal to, again, the density of the liquid it's pushing away times the volume of the liquid it's pushing away times gravity. This is why, for instance, when you try to push something down into the water, do you notice that it gets harder to push it down the more it gets submerged? The reason for that is the volume that you are now pushing out of the way is increasing. And so when something is submerged completely underwater, like in this case, the whole volume of the thing is creating buoyant force. But you can have cases where you have partial buoyant force because only part of the object is underwater. Okay. Maybe that helps a little bit about where it comes from. But I'll explain it more as we get into more buoyancy stuff. This is a funny diagram. All right, let's go see on the queue. What do we got? 32 questions. Okay, let's go choose a winner.
Let's go gambling!
Oh, who's it going to be? Dan George. Nice, Dan. You submitted an hour ago, and you had an 8% chance. Congrats. Ooh, yes, here we go. Oh, this is a hard one. Yeah, this is exactly what I wanted. Really? This was on the practice FR. Dude, this one sucks.
Oh, no.
Emotional, damn it.
Yeah, here we go. This is a Bernoulli's question for sure. Shahir's like, no. Okay. This is something. Okay, if they're gonna ask what I think they're gonna ask, this is gonna be. Oh man, this is what you would ask in a college level class. All right. A large container is filled with water. The container is filled to a height d, as shown. A release valve is opened at a height little d above the floor, and water exits horizontally from the valve and initially hits the floor a distance x from the side of. Yes. So yes, you could use Torricelli's law to just do this. It's kind of cheating, but sure. Assume the water in the container is still. The effects of friction and turbulence are negligible. Great. So yeah, Robert, do you get that equation in your Yes, yeah, in V10 because the air. Yeah, do you get that on the AP test? Do they give you Torricelli's law, which is this? This is the simplification. V is equal to the square root of 2gh. That tells you what the velocity of the water is coming out of the valve. But I don't know. The full way to do this is to do, you don't get it? You have to derive it. Okay, so this is where it comes from. I'm going to show you guys. This comes from Bernoulli's equation. Which says that P naught plus 1/2 rho V squared plus rho GH has to be constant. So we can think about it in two situations. Let's call this like situation A, which is like outside. Let's say A is outside the valve. And then let's call this situation B, which is like you're inside the valve. I'm getting a 2 max? No. No, you're gonna do okay. Nah, chill, 5 minimum. Okay, so this is what we do. And I'll explain all the terms here. This term right here is called like the background pressure, which a lot of times is referred to as atmospheric pressure. Okay? I assume this is I think we assume that this is open, right? Okay. So this right here is like background pressure. Which P naught is equal to P atmospheric if open to air. Okay? So in this case, in situation A, when you are outside the hole, you are open to air. You see the atmosphere. So that's going to be P atmospheric. Plus 1/2 rho times the velocity of the water coming out of the valve at situation A. So we can say like VA squared. Okay. And then plus rho GH, which is how high the water is, I believe. Okay. So the height of the water, I think, is rho G times D. We're going to say rho G D, right? I'm measuring all the height here from 0. Yeah, all good, dude. Yeah, I mean, retaking stuff is okay as well, especially if you want to get a deeper understanding for it. Okay, so now let's look at situation B, okay, which is the water inside. What we're trying to do is we're trying to figure out what the velocity of the water is exiting here. So then I can do kinematics to figure out how far it goes before it hits the ground. So in situation B here, we assume that the container is also open to the air. If it wasn't, this would be a different question. Then rho naught would be 0. P naught would be 0. We assume this is open. Okay. So I'm going to say, okay, cool. This is equal to, and since it's open, it's also P atmospheric. And then we're going to say 1/2 rho, the velocity of the water, VB squared. And then this is going to be plus the height of the water, which is going to be rho GD. Big D, right? Okay, here's the key thing here. They say assume the water in the container is still. Because of this, you can assume that VB is equal to 0. You can assume that the water is not moving very much here compared to how fast it is moving here. And that's because there's so much more water here than there is coming out here, and that also goes to this concept. So A1V1 is equal to A2V2. So we would say V2 is equal to A1 over A2V1. And since the area of water here is so much bigger than the area of water that's coming out of the valve, this is basically 0. So that's where it comes from. Paul says, I put D for the height. I put big D for here, I think, right? I think that's okay. Oh, wait. Is this supposed to be D minus big D? Because I think you do the amount of water that's above it. Oh, in that case, this is 0, right? Yeah, sorry. Okay. Well, wait. I think you can still talk about the water up here as being rho GD, right? Yeah. Shahir says yes. Yeah. Yeah, I think you can still do that. The rho only matters if the density changes along the way. Yeah, I don't think it does it either. Okay. So anyways, so this tells me that VB is 0. So this is going to go to 0. And then these are going to cancel. And then so... Okay, wait a minute, one sec. I think this has to be I think this has to be big D minus little d. I think that's what it has to be, right? Wait, no. I eventually want to just get rho GH. No. Shahir, tell me which one it was supposed to be, sorry. I always mess this up with the height. I hate the height. I hate the height, man. No, I think this is fine. I think it's fine how it is. Yeah, okay. I got this. Because I think this refers to the height of the water that's above you. Yeah. Right. Okay, here we go. Solve 1/2 rho VA squared is equal to, and then this is going to become gamble. Yeah, rho GD. Good, yes. Minus rho G little d. Okay. Now the rows cancel. Goodbye. Okay. So then you get VA squared is equal to 2G big D minus little d. And so VA is equal to the square root of 2G big D minus little d. Which, yeah, is the same as this. Yeah, it's D minus little d because you're solving for the values to the atmosphere above. Exactly, right, yeah, okay. So yeah, and that's this, I think this refers to the height of water above. Above the hole. Yeah. Which, in that case, is that is big D minus little d. Right? This is H, which is equal to big D minus little d. Where did the G come from? G came from this. So in Bernoulli's equation, the third term is rho GH. If I know nothing about fluids, should I focus on mastering other concepts? I think you should try to learn a little bit of fluids. I think the number one thing, which is very easy to maybe pick up, is just the concept of buoyancy and weight. Or like force of gravity and force of buoyancy. That's what came up on the FRQ last year for fluids. So just understand that. This is hard. I hope they really don't do this. This is a hard question to do. I hope they don't do this to you guys. Yeah. Oh, didn't the G's cancel out? No. So this moved over here, right? So you had rho GD, rho GD. There was no G on this term here. So I just factored out the G, is what I did. And then I canceled the rhos. Okay. So there you go. So this is the velocity of the water that's coming out of the spout. Right here. Out of the valve. And then, what do they want to do? They want to know, okay, what is it? Oh, well, I think you're missing the parts for this, but what they want you to eventually solve for is X, which is how far it goes. And so now this is just a kinematics question. Yeah, the rhos canceled out, exactly. Yeah, okay. So here's what happens. This is at a height of little d, right? And then you have, this is just a projectile question, right? Now this is going at a V naught, which is equal to square root of 2g d minus, big D minus little d, right? So then if you want to figure out how far it goes, right, that delta x, you know that's equal to V naught times t, right? Because this is only in the x direction. Okay, so now you just need to figure out t, which is the amount of time it takes for this to, like, fall down. That's kinematics. You should just know right off the top of your head what it is, but it's okay if you don't. So, x equals x naught plus v naught t plus 1/2 at squared. So, you're going to say 0 is equal to d. That's all 0.
You're not that guy, pal. Trust me. You're not that guy.
And then this is minus gt squared over 2. Right, acceleration is negative gravity. Cool. So then 2d over g, 2d over g square rooted is equal to the time. If you solve for time. So that's the amount of time that the water spends in the air before it falls. And then that time is multiplied by the velocity in the x direction when it leaves the hole in the cylinder. So delta x ends up equaling square root of all of this times this. So you get 2g big D minus little d times 2d over little g. Cancel, cancel. So you get 2 square root, because 2 times 2 under a square root is just a 2 on the outside. And then that's d minus little d times little d. Yeah. X equals v. Wait, what? Sorry, what? That's solving for t in terms of y. Well, I mean, it's the same thing. Yeah, double square roots, even better. So I believe this is the answer. I think you just get square root of x is equal to 2 square root of dd minus d squared. Seems kind of weird. One sec. Let me throw this in the chat GPT. Oh, it's cool to see what chat's got. Solve for x. Go. It'll figure it out. Yeah, there you go. So 2g big D minus... So they skipped right ahead to Torricelli's law. You don't have this on your equation sheet, so you have to rederive it from this. And then let me make sure they got the time. Yeah, look, and time is 2d over g. Great, cool. There we go. Yep. Same answer. Nice. Great. That's a really good fluids question. That's a really good fluids question. Thank you, Dan George. It's a really good fluids question. Okay, personally, I don't think that's going to come up on the AP exam because that is very involved. It's a great college level question. It's something I would give to my class at UCLA if I was testing on fluids. I would give a question like that because it involves mechanics. It involves, you have to know Bernoulli's equation. You also have to know the approximation for like the mass flux. So I don't think it's going to be that bad. Shahir says mine's an expanded version of that. What do you mean expanded?
Oh no.
I don't think anything's going to be harder than this. This is too much. They're going to be nice on you, right? Yeah, right? Not going to be too mad. Who knows? Okay. Okay, so Dan George. But not to worry. If you didn't understand all of that, here, and I'll put more time on the timer for you guys. Because you guys do have like 30 questions in the queue. There you go. You can have another hour of my time. Okay. If you didn't understand all that completely as we were going on, I'm gonna put the screenshot for it and also the recording for it. Yeah. Let's go. What did you need to see, Mila? What do you want to see? Can you show how X was gotten? Yeah, totally. I can go show that. Here, I'm gonna put that there. Okay. So how was X gotten? So once we figured out the velocity of the water that was exiting here, to figure out the distance that it travels before it hits the ground, this is a basic kinematics question that you guys have learned from here. So I know I have an object here that's located at a height little d, and it is traveling outwards strictly in the horizontal direction at first with this velocity. Okay. I know if I want to figure out how far it travels before it hits the ground, like how far it travels in terms of x, I need the velocity in the x direction times the time it spends in the air, okay? Because the velocity in the x direction does not change as it is falling, because there's no forces in the x direction as it's falling. So that's this, okay? And then you need to figure out the time that it takes for it to fall. You should try to just memorize this. This is free fall time. So this is how long it takes something to hit the ground when it's just dropping from rest from a height d. And so yeah, good. Once you have that, you do this for t, you do this for this, combine some radicals, and then you get to here. But yeah, if you didn't follow that exactly, in the Discord under homework help here, you'll see it. It's Dan George's question, but we have the screenshot of all the work, so you can go look at that. And then also there's a timestamp, so you can go back and watch the recording for it. So go check that out. If we skip the Tornicelli, do we lose points though? I don't think so. I think you'll be okay, because that's a really time-consuming question. I think if you lose points, you might lose a point or two. I think that's an okay thing to kind of memorize. Any formulas not on the formula sheet you recommend we memorize? I mean, there's 1,000 of them. I mean, the Torricelli one definitely comes up a lot, and then yeah, whatever this one comes up a lot for free fall time. I think as we see them, I'll point them out if I think like that's a great one. What are the FRQ predictions? I don't make predictions. What? Is this in Calci or Polymarket? Is there a Polymarket for the AP exam predictions? All right, let's go see. What else we got in the queue? 38 questions. Jesus Christ. Okay, great. Okay, let's go. Spin the wheel. Who's gonna win?
Let's go gambling!
Lawson! Congrats, Lawson. Oh, wow. Oh, wow. More fluids.
That's dope.
More Lawson. More fluids. Yo, that is luck. Yeah, Lawson, you've won it twice, dude. You had a 2.3% chance, apparently. That's what the probability says. Okay. Water fills a pipe of radius r and has speed v as it exits the pipe. The water flows into a large rectangular pool of length, width, height, as shown below. Which of the following is equal to the time it takes for the pool to fill the water from the pipe? Oh, fascinating. Oh, this is the radius it's coming out with? And a speed v? Oh, very cool. Okay. So, oh man, I don't want to get too much into the calculus of this, but let's talk about, can I talk about volume flux? Is that okay? Does that word scare people? Volume flux? Or volume flow rate, maybe? Okay, flow rate formula? Okay, let's do that. Okay, so flow rate. Because I want to say like dVdt. I want to say this. I want to say delta V delta T is equal to area times rate. You guys just get AV equals AV? Okay, that's another way to say it. Okay, we can say it too. Okay. Okay, so A times V is equal to volume flow. Are we cool with that? So this is equal to volume per unit time. I realize there are two V's. This is velocity. Flux capacitor. Okay. So this here is area. And then this is velocity. And then this is the volume of water. So it's like the 3D amount of water per unit time that's moving somewhere. So in this case, the volume flow is equal to the area of this pipe, cross-sectional area, which they say, well, they say it's a pipe of radius r. I assume it's a fucking circle then. Okay, fine. Okay, so this is pi r squared, and then times v, which is the velocity. Okay. That's equal to the change in volume over the change in time. All right? Now, they want to figure out how much time it takes to fill the pool, okay? So that means the volume of the pool that needs to get filled. This is the pool that needs to get filled. We'll explain which one it is. The pool that gets filled, that volume is length times width times height. So that volume is equal to length times width times height. GG's. Okay. So pi r squared v is equal to LWH all over the change in time. So I'm going to flip C, put that over there. And so I'll get that the change in time is equal to LWH over pi r squared v. Yeah, okay. I think it's answer choice B. That makes sense to me. Wait, did I do that right? No. Sorry. Answer choice A. I'm dyslexic today. Okay. It's A. Yes. Cool. If you get seconds on the top, and then this is meters times meters squared, which is meters cubed, and then this is meters times meters times meters. So this is meters cubed. So meters cubed, seconds. This answer gets you seconds. Just by the units, right? If you were like totally screwed, you could just say like, okay, which one gets me the right units? This one gets you 1 over seconds.
You're not that guy, pal. Trust me. You're not that guy.
Oh, did my stream lag? Oh, I'm sorry. Sometimes it lags. Okay. Let me make sure my stream's okay. Okay, cool. Yeah, is our stream health okay? Yeah, it says we're okay. Okay. Yeah. So, yeah, this is frequency, which is wrong. This is another case, right? This is meters per second. Also not right. This is also... This is meters to the 6th over seconds. So, Yeah, if you don't even know any of the equations, sometimes just look at the units. You know you need a time for it to fill the pool. This is the only choice that gets you seconds as a unit of time on the top. Yes, F is 1 over T, T is 1 over F. Yeah, that's for simple harmonic motion. Correct. So this would be the answer. The other way to think about that, yeah, that's simple harmonic motion. I mean, that's a true thing. The other way to think about this is look at what should happen. So as my velocity of water that's going through the pipe goes down, what should happen to the time? The time should go up. So look at these in terms of like just what happens in the extreme values. If V goes down, time should go up. That doesn't happen here, right? If V goes down, the time goes down. It wouldn't make any sense for the thing to fill up faster if the water's flowing slower. Same thing here, same thing here. Like, yeah, you can instantly just mark these wrong as well. So this is the only one also where like as the volume goes up, the time should go up, right? If there's more rectangle you need to fill, there's got to be more time. So great, cool. All right, good question though. It's a good one. I can't wait to just go relax and go fishing after the stream. Yeah, it's so nice. All right, good job, Lawson. It was a fun one. Oh, I can't wait to eat some dinner. I haven't eaten like the last 4 hours. Also do torque. Submit a torque question. I might do it. All the questions we do get put in Discord, so go check them. They're there. We've been doing a lot of fluids today. Well, I think because that's the thing most of you guys are scared about, because some teachers just didn't even teach it, right? All right, let's go pick another winner. And it's a new thing for the exam, so I understand.
Let's go gambling!
Neil Wanzer. Oh yeah, this is another good one. This is pressure. Okay, hydraulic lift is used to lift a car. The small piston has a radius of 5 centimeters and the large piston has a radius of 50 centimeters. If the driver applies a force of 88 newtons to the small piston, what is the weight of the car the large piston can support? Oh, interesting. Okay. Cool. So I think you want to figure out what F out is. And this is cool. This is how hydraulic jacks work and stuff. So the key concept to know here is that pressure is equal to, I want to say it's force over area. Right? Yeah. And the pressure of this liquid needs to only really depend on the height. Yeah, Pascal's has something to do with this, yeah. So notice how here, right? As long as the fluid is incompressible, pressure equals constant. Kind of the same thing here. So here as well, the pressure within the liquid needs to be the same. So the pressure is going to go as the force over the area. So I can say like P1 equals P2. The forces won't be equal. No. So the pressures have to be equal though. Yep. So I can say that like F1 over A1 must equal F2 over A2. So then F2 is equal to A2 over A1 F1. F1 is 88 newtons. And then here are the areas. So area 2 had a radius of 50 centimeters. So that's going to be pi times 0.5 squared. And then this one is pi over 5 centimeters, so 0.05 squared. right? Because area is equal to pi r squared. Yep. I did put it into meters. Good. Yeah, I put it into meters. So this cancels. And then this is the same thing as, I don't know, you could write this as 5 times 10 to the minus 1 squared over 5 times 10 to the minus 2 squared. I'm going to do this without a calculator. So then that's 25 times 10 to the minus 2 over 25 times 10 to the minus 4. And this is all times 88. So this cancels as well. And then 10 to the minus 2 over 10 to the minus 4 is the same thing as 10 to the 2 times 88. So then that's 100 times 88. So 8800 is 8.8 thousand. That's another way to do it. Yeah, answer choice C. Good. Very good. It's over. It's not over, Jay. Got you, Jay, dude. It's fine, dude. Stay strong, buddy. Okay. Did I not say 8800? Oh, I put too many 8s.
Oh, nice.
Emotional, damn it.
Man, I hate when I do that. Yeah, I put too many 8s. Yes. I chose the right answer. I'm getting sleepy. We're at the 4-hour mark at this point. I once did a 24-hour stream. I did a tutoring stream for 24 hours. Holy shit, dude. I was hallucinating by like hour 16. I was hearing things and seeing things. It was really weird. But I definitely start making algebraic mistakes after like hour 4. You have a snow day tomorrow, canceling your exam. Lucky you. But I heard the retake is sometimes harder. But yeah, stay safe with the snow, man. It's the Torcelli's graveyard. I don't know if I want to go to the graveyard, man. That doesn't sound like a good place. All right, this one was Neil. Let me put it in our Discord. Nice. That's a good question, Neil, by the way, for fluids. Yeah, that's a good one. Pascal's principle is what that is, yeah. Okay. Let's go spin the wheel again. What are we going to get?
Let's go gambling!
Where's the torque? Where's the torque? I don't know. It's somewhere in that wheel, dude. It is somewhere there. Reebs. Let's see if someone submitted a torque question. This is close. This is, it's kind of like, it's a circular motion. We're getting closer. Okay, here we go. All right. A meteoroid is in a circular orbit with 600 kilometers above the surface of a distant planet. The planet has the same mass as Earth, but a radius is 90% of Earth. Okay. The acceleration of the meteoroid due to the gravitational force exerted by the planet is most nearly... Oh, okay. What's a Reebs? I don't know what a Reebs is. Okay. Okay, so planet. Let's draw planet. And then we say bum, 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 bum. But they just want they want the approximation of it exerted by the planet. Okay, well I can immediately get some wrong, right? Okay. Yeah, watch here. We can just do this. This is the meteoroid, right? Right. The correct way to do this is the force of gravity is going to be equal to big G m1 m2. But they don't tell me the mass of the meteoroid. I think we assume it's small, I guess. And then R is technically here. This is like R, and then this is like H, and this is big R squared. But big R is equal to little r plus little h. Yeah, so this is G m1 m2 over r plus h squared. Okay, I think what we're going to do well, first of all, the gravitational force of attraction for something on Earth that's basically at the surface. So here, for Earth, if you have an object that's basically here, basically on the surface, the force of gravity is just equal to mg, and so acceleration is just equal to negative 9.8. And that's towards the center. This is an object where the planet is less than the mass of the Earth, so gravity is going to be lower. Also, the meteoroid is not exactly on the surface. The meteoroid is 600 kilometers above, but the Earth's radius is 90% as much. Oh, so this is actually pretty cool, because 10%, so the 10% difference is 637. So, oh, this is super cool, actually. So the meteoroid is effectively at the same distance as an object would be from the center of the Earth if it was close to the ground. So, okay. Dun, dun. It has the same mass. I think it's gonna be... I think it's this. I think it's C. Yeah. I'm pretty sure it's C. It's the same. It's the same as Earth. Right. The reason for this is this R was equal to 6370 minus 637. And then this was 600. So it's kind of the same as if something was located 6370 away, which is just 9.8. It's towards the center of the planet. Yeah, it's answer point choice C. Cool. That's a good question. It's a fun one, Reeves. You're goated and you're guessed. Good. Yeah, always guessed answer choice C, right? All right, nice, Reeves. Let's go do another one. Choose a winner.
Let's go gambling!
So it's always trying to pull these things. It's always trying to pull things together towards each other. So it would always be towards the planet. I don't think it would ever be like towards the asteroid. That would make so simple. Larry the Lobster. Oh man. I got edged. Dumb.
Aw, dang it.
Okay. Is this an AP Physics 1 question or is someone like just trying to troll me? A spaceship is sent to investigate a planet of mass m and radius r while hanging motionless in space a distance 5r from the center. Spaceship... Okay. The ship fires an instrument package. This is pretty extreme. Larry the Lobster. With a speed v0 as shown. The package has a mass m, which is much smaller than the mass of the spaceship. Cool. For what angle theta will the package just graze the surface of the planet? This is not Physics 1. Yeah, this is not AV Physics 1. Yeah, bro. I have to deal with gravitational potential at this point, right? Yeah. Yeah. You have to have... Oh, man. Because as this thing gets closer, right, it's going to get pulled further in. Larry, chill. Here. I've never... Yeah, it's okay. Here, I'll put this in ChatGPT just to, like, see. Just to see if it was. I don't think it is. I think you have to deal with gravitational potential. I'm not going to, like... I won't spend time doing it because I mainly want to help AP Physics 1 students today. But it's cool. I'll put it in my Discord for another time to solve. I think you need calculus for this. Yeah. Well, actually, not exactly. It's a little involved. It's actually, yeah, it's just conservation of energy. But then angular momentum as well. Yeah. Okay. I don't think this will get asked on the AP Physics 1 exam, but here, I will give you the link for it at least. Just in the... do I do Calculus AB? So I teach everything. So my streams, I help questions of all sorts of math and science and whatever. So I tell people, come on by to those. I'm not going to have a specific AP Calculus one. But if you want to figure out all the other times we stream, we have a schedule here. The same website you guys are using to submit your screenshots. If you click on streaming schedule, this has the schedule of what we stream. You can see we're severely over time. I think I'm going to go 5 hours today from what I was scheduling to do. But tomorrow we'll be on at 5 o'clock. We can help you guys. Can you please help me with torque? Okay. If your torque question gets selected. This is cool. I like this question, but I just don't have the time to explain it. But come on by, Larry. I put your question in our Discord here. And then here's the ChatGPT explanation for it. I'm happy to explain it during another stream. Okay. What do I write on FRQs if I don't know anything? Write down equations that look like they're related to what the thing is. Yeah. That's the least you can do, man.
Let's go gambling!
Okay. I can't even see the names. It's Jack Ma. Oh, the founder of Alibaba? Really? We got the Alibaba here? Okay. I think this is another extremely difficult one. Or maybe not. Do we think so? Just exclamation point Discord. How's it? I get the feeling this is not an AP Physics 1 question, though. A disc rotates with a constant angular velocity, 2 masses, slide without friction in a groove passing through the center. They're connected by a light string, initially held in the catch with a mass ma at the distance r. Neglect gravity. At t equals 0, the catch is removed and the masses are free to slide. Find r double dot immediately after the catch is removed. Yeah, I'm gonna say this is not an AP Physics 1 question. Again, I'll throw it in chat. Yeah. I just want to see the solution. I can tell real quick whether this is AP Physics 1 or not. The fact that there's r double dot, yeah, is... yeah. I don't think so. Yeah. Not quite. This... you'd have to do with... I'm trying to think. R omegas, set them equal to each other. Yeah. Yeah, don't worry. Yeah, don't get scared by this, guys. That's not something you have to do. Okay. Cool question, though, Jack. Again, I'll go through it on another stream when it's not... AP Physics 1 is tomorrow. The dots mean derivatives. Yeah, so if you guys want to... I mean, this is a good little heads up, not to scare you guys too much. The R double dot means the second derivative. So they're asking about the acceleration of... the acceleration. So m r double dot is the same thing as mass times acceleration of the object is equal to... this is m r omega squared. This is... oh, man, what is that? That's... r omega is v... I think this is... okay, this is centripetal acceleration. Yeah, this is centripetal acceleration times mass, and then this is tension. So these are two forces. And then this is another set of forces. So it's cool, but you don't need to know it for AP Physics 1, don't worry. Alright, let's do another one. Someone give me something that's like AP Physics 1 appropriate, please.
Let's go gambling!
It can be that. Those are also valid ones. Trojan horse. Okay, Trojan horse. No. This one's also a little too tricky. Try it again.
Let's go gambling!
I might go through and just go find who has a torque question. Grinch. Let's see what does Grinch got for me. me see. The pendulum activates an escapement mechanism. Every time the escapement is under tension and gives a pendulum. No. No. Okay, someone submitted. I now know why the queue is so long. Someone's giving me a bunch. These are all really hard questions. Like, we're not dealing with this. Okay, I'm gonna go find a torque question. Just do the damn question, bro. Is this torque? No. Almost torque. Gravitational potential energy, sandwich man. Not quite torque. I want someone to give me a torque question. Oh, someone put in a bunch of really hard physics questions just to troll us. Yeah. You know how I can tell? Because they're all coming from the same book. Because, wait, what is question 8.3? Milas has a torque one? Okay, let's go find Milas's. Where is this? Mila? Good. Yeah, let's do this. Cool. I'm going to do this one with you, Mila. It's great. We'll do it. Good question. Got you, Mila. Okay. All right. Yeah, Shahir. Let me do some torque ones because they've been asking for torque, and then we'll get back to doing fluids. Okay. The left end of a uniform beam of mass M and length L is attached to a wall by a hinge, as shown in Figure 1. One end of the string with negligible mass is attached to the right end of the beam. The other end of the string is attached to the wall above the hinge at point 1. Okay. The beam remains horizontal. The hinge exerts a force on the beam of magnitude FH, and the angle between the beam and the string is theta 1. The following rectangle represents the beam. On the rectangle, draw and label the forces exerted on the beam. Draw each force as a distinct arrow pointing away. Okay, great. Cool. All right. So you are going to have tension from the string. Force diagrams, yep. Okay, so this is force of tension. Or you want to say, yeah, let's say just tension. Okay, that's from the string. And then you're going to have the force of gravity. From the mass. And so that's going to act at a distance of exactly halfway. This is going to be L over 2. Yep. And then what other forces do we have? Oh, we have the hinge, right? Okay. And then we have the force of the hinge, which could be up or down, but it's definitely going to be at least to the right. So I think I want to say this. I think I want to say force hinge. There's a reaction force by the rod. Yeah, at this point, I think, right? It's up. Yep. I think it's up as well. Okay, great. Okay, cool. And then what was part B for this one? Oh, and that's it? You don't have to solve for it? Oh, that's nice. Someone says it's down. The hinge force is down, you think? Wouldn't it be opposite FT? I mean, it is opposite left, right. I forget if it's up, down, or if it's up, down, or is it? Let me think. I know you're gonna have torque. Well, that actually doesn't matter. The force on the change, yeah, the x component, which is FT. Okay. Let's figure out whether it is. We can do this. We can do this with math, right? If we look at the forces that are acting on this, it's gonna have an up-down force from here. The answer key is definitely up. So my chat is conflicted. Some say up, some say down. Let's figure out what it is. So this would be FTX, which is equal to FT cosine theta. And then this is going to be ft sine theta. Right? So let's look at what the sum of the forces would be in the y direction. So I think you'd have ft sine theta. And then let's assume for now that fh is positive. So I'm going to say plus fhy. And then I'm going to say minus fg. Okay? And then the sum of the forces in the x direction, well, you're going to have fhx pointing to the right. And then you're going to have minus ft cosine theta. Okay, and then all of these forces are equal to 0. This is a statics thing. Now let's look at the sum of the torques. Or I think you guys do it like this way. Okay, so if I choose this as my rotation point, so I don't even care about this torque, then I have this pulling it this way, so that's positive torque. So I would say ft sine theta. So I want the amount of force that's perpendicular to the radius. And then that's going to be times L. And then minus the force pulling it down in the clockwise direction. And so that's going to be minus Fg times L over 2. Okay, cool. And then this also has to be equal to 0, yeah? So let's see if we can... We're talking about the ledge side? Okay, so here. I think from here I can determine whether it has to be positive or negative. Yeah. Okay, I'm gonna rewrite this as ft cosine theta has to equal fhx. And then I can rewrite this as ft sine theta is equal to fg over 2, right? So if I move this over, I get fg L over 2, but then I'm going to divide by L again. So then I get this, yeah? You don't get how I found torque. Okay, totally cool, totally cool. Okay, so things are rotating about here, Mila, right? So if I have something like this, right? Things are gonna it wants to rotate this way. I'm gonna say this is the pivot point. Torque is always equal to the amount of force. So in this case, that is perpendicular to what your distance is. So in this case, the string exerts a torque that's trying to pull it this way. And that's positive torque. And that torque is equal to R times, I say like F perp. And so F perp, in that case, is Ft sine theta, because that's the amount of the string tension that's pointing up and down, which is directly perpendicular to left-right for the radius. And then, yeah, the radius is L. Thanks, mathematician. Appreciate you, dude. And then there's another force of gravity that's acting at the center of mass of the rod. And that force pulling down is mg. So I just wrote Fg here. And that is pulling it clockwise, which is technically negative torque. So we'll put a negative sign there. And the distance that acts at is L over 2. So that's why I got this, which I could then rearrange to get this. So then here's actually the cool thing. I can then take this. So this came from this, this came from this. I can take this and plug it into here, right? So let's see what we get. So, right? So now I get from this, plugging it into here, I'm going to get that FG over 2 plus FHY minus FG is equal to 0. So that tells me that FHY is equal to FG minus FG over 2, which is equal to positive FG over 2. And that's how I know that the force on the hinge is pushing up. No, you're okay, Mila. Where did the 1/2 come from? So the 1/2 comes from... So when we think about the force of gravity acting on an object that has a certain length, we can imagine this object as a single point mass, like a single small object that has mass of the entire thing, but it's located at the center of mass of the object. And so this is the midpoint of the length of the rod. The length of the rod is L, so the midpoint is L over 2. Thank you, Jay.
Good job.
Does that make sense, Mila? Because then torque is all about where does that force act. So it acts at a distance L over 2 from the rotation point. And then this is the force of gravity going down. I'm glad you're here. Yeah. Does that make sense, Mila? That's where this came from. This is the distance. And this is the force on the rod. Yeah. So then what I did was, from this, I got an expression for ft sine theta, because what I noticed is that there's an L in both of these. So I can just cancel it out. And then I can move that over. So I get FG over 2 is equal to ft sine theta. But then in my original sum of forces in the y direction, remember that like ft sine theta plus what this FH was had to balance, so all the up forces had to balance the down force of gravity. This is not torque, so I don't care about where it acts. I just care whether it's an up or down force. Now I can replace this ft sine theta with the expression I got for ft sine theta from the torque. And so then this is FG over 2 plus FHY minus FG is equal to 0. And so if I move this over and I subtract this over, I get that the force of the hinge in the y direction is positive force of gravity divided by 2. Jimmy the Bob has another torque one? Okay. So anyways, yeah, so that's why I know the force on the hinge is upwards. I had like a guess that it was, but you can do the math and you can figure out that it has to be. It's kind of cool. Okay. Let me see what they would do here real quick. I think we can just like derive things real fast. Do you think this is guessable? I mean, anything's guessable if you try hard enough.
Oh, no.
But no, you want to understand this. It's not too bad. There are more parts. Always take AP Physics. AP Physics is great. How about Unit 1, guys? What's up with poor torque? Let's start at the beginning. Okay, so then they say they decrease the string, and the beam remains horizontal. The angle is lower. The magnitude of the tension in the string is that... So what's the magnitude... So what happens to the tension as you move it lower? I believe the tension goes up. So let's see kind of where that comes from. So... Remember that FT... From our expression here, from when we did stuff with the torques, we had that FT sine theta was equal to FG over 2. Okay? So that means... So since the force of gravity acting on the rod is always the same, FG is always the same. It doesn't matter what angle the string is that's trying to hold it up. So here's what I would say. I would say so FT sine theta is equal to FG over 2. So if theta goes down, sine theta goes down, and then FT would have to go up. The other way to think about this is, without using formulas, is, so this string here is providing force in the upwards direction, which is counteracting the force in the downwards direction, or let's say, like, think about the torques. The upwards force, the upward component of this force is the only thing keeping this thing rotating up, because force of gravity is trying to keep this thing rotating down. If I decrease the angle at which I'm attaching the string, now even less of this tension is pointing up to keep it going this way. So if you're decreasing the amount of y component that this tension provides, then you need to boost the tension, because it still needs to provide the same amount of torque to counteract. So I would say this. I would say, like, still need same amount of torque to counteract the torque from gravity. But torque is equal to Ft sine theta times L. So if theta goes down, Ft must go up. So yes, it does increase in the x component, 100%. So what ends up happening is you're going to increase the force in the x direction, so FHX, so the force of the hinge in the x direction will increase, for sure. Cool. Okay. And then you could derive an expression for the magnitude of the tension. That would come from this. Oh, we already did it. Wait, we already fucking did it. That's this. I would just say Ft is equal to mg over 2, 1 over sine theta. Done. We already got that from this. Okay, cool. Nice. Good question. Let's see, which question was that yours? Mila, you were number... I'm trying to figure it out. Mila. Number 3. Yeah, don't out his school. Okay. Let me just manually look through the queue, because yeah, I do have to cut it after this time. So we got like 20 minutes left. What where's yours, Shahir? Let me see. How much crazier is yours? Oh, so you have the same thing here. It's the same question, Shahir. So we did this, right? We did this. We did these first two parts, right, Shahir? Oh, okay. This is not too bad. One sec. This here, I'm just gonna add this part to. I'll just add this part to what we had here. It was here, right? This was the same question we had. Because it said when the container is filled to a height d, the speed of exiting the water is v naught. Sketch the graph of the speed of the water leaving the valve as a function of the height of the water of the height of the water in the container. Oh, so that's just this, right? So the height of the water. Why did they put D here? What? It's kind of weird how they did this. So this is just square root. So I guess eventually... I'm trying to think how this works. You have a decreasing square root. I think it'll just look like this. I think, yeah. Yeah. Yeah, it's an expanded version. But that's what it is, right? Because as D goes up... Sorry, is the height of the water... Why are they doing it this way? Sorry. Oh, okay. Oh, so it's okay. It's 0 when little d equal. Okay, when big D equals little d, it's 0. Sorry, and then it's this. This is what I wanted. Yeah. Yes. Okay. Sorry, I was thinking about it's going down. It was like fucking me up, dude. Okay. Suppose the container is filled with salt water, which has a greater density than fresh water. How will this change the horizontal distance? I don't think it does. I say it doesn't, right? It doesn't. Yeah, it's a root function, yeah. Right, it looks like that. Right? Because none of this shit depends on mass. So who cares? Yeah, cool. Cool. It doesn't. Yeah, that's cool shit here. Alright, let's see. Let me get through all this stuff we already had. What happens if I don't know any material besides the basic physics? Density is independent of speed. Yeah, correct. Okay. Ooh, this is fun. Buoyant force? I think they're all equal to each other. This is another good one. Someone's asking about this. I think this was Lamberry's question. Can we do Jimmy the Bop? Yeah, alright, we'll do Jimmy the Bop next. Let me do this one real quick. I got 12 minutes. Just go learn torque. It's not that bad, man. There's plenty of resources. So they have a solid prism. The prism can be placed in the tank. And the prism sinks to the bottom. Fx is the magnitude of the buoyant force. Fy and Fc. Which correctly ranks the magnitude of the 3 buoyant forces? Are these not the same? Because I thought force buoyant is just equal to rho naught V times G. I wasn't planning on doing a Physics 2 review. I mainly only did this because someone asked me to do it for Physics 1. But that being said, I will be live streaming tomorrow. So if you want to ask Physics 2 questions, you totally can. The website for that is the same website you guys are submitting screenshots. Just go to the schedule. It'll show you when it is. Yeah, they're all the same. Great. Okay, cool. Right. Doesn't care about orientation. There is a difference, I think, probably in like the normal force maybe, or like the normal pressure or something. I forget. But yeah, all the same. Okay. Let me put that one in. Okay, cool. The lab question. Okay. Let me see. Someone asked me to do something with torques. 2017, dude. Yeah, dude. I'm gonna come after you. Whoever was submitting these questions, I'm gonna come after you, dude. Where's K-Bop? Where's K-Bop? You guys were talking about. Oh man, Jimmy the Bop. That is not a torque question. God damn it. Y'all always find ways to troll. Okay, let me find Shahir's other one. Okay. People have been asking me about lab questions. I will do these. Bruh. Okay. Okay. A group of students are given a glider and a track. The track is leveled and turned on so that the glider floats gently on a cushion of air, shown in Figure 1. The manufacturer of the glider track claims that when the track is turned on, friction between the glider and the track is negligible. Students want to determine whether the manufacturer's claim is correct. Indicate what quantities could be measured by students that would allow them to determine whether the claim is correct. Okay. Okay. So, if there's no friction, right, then there shouldn't be any opposing force that causes deceleration. So I think the key thing here is always indicate, like, what are you trying to figure out, right? We're trying to indicate whether the friction is negligible. So I would say trying to prove force of friction, right, is equal to 0. Well, where does force of friction come up in? All right. Well, I know from the sum of the forces on an object, right, has equal to the mass times acceleration. So if something is just like chilling and moving at a constant velocity, then the sum of the forces must be equal to 0 because the acceleration must be equal to 0. So that would mean that the force of friction would also have to be equal to 0, right? So what quantities could be measured? I would say position versus time, right? Because if position versus time is constant, then the velocity is constant. That means the acceleration is 0, which means there's no force, right? Briefly describe a method. Anytime they say this shit about, like, oh, how would you reduce uncertainty? Just say, like, many trials. Just be like, I would do this over and over again. You can say many trials, or initially pushing the whatever, is it a ski? What do they call it? The glider at different speeds. Yeah, you can calculate ideal acceleration versus real acceleration. Well, ideally there should be no acceleration, right? You should push it and then it should have no acceleration if there's no friction. It shouldn't slow down. Yeah, repeat to reduce error. There you go, ampersand. Yeah, just make them happy, dude. Just say, like, many trials. Indicate what quantities a student could graph on the horizontal and vertical axis to create a linear graph that can be used to determine the claim is correct. Good. So, if you want to show acceleration is 0, right? Then you want to show that position versus time is linear, right? Or I guess that would be determining, like, whether, like, r squared fits a linear graph. So let's do this. Let's plot velocity versus time. Velocity versus time should have a slope of 0. I think that's really what we want to graph. So yeah, instead of saying position versus time, well, we could measure position and then we could derive velocity from that. Yeah. I need help with my physics exam on Tuesday by private tutoring. I'll pay you $250 per hour from you. Stop. Can't buy my soul, dude. Do you need my Cash App? Yeah, there you go. Okay. Cash App is always scams. All right, great. So, yes, if you graphed velocity versus time, slope should equal 0 means acceleration equals 0, which means F friction is equal to 0. Okay? That's, I think, what you want to say. And then, yeah, this is what you would say. Yeah, cool. I would say delta V, delta T is equal to acceleration, which is equal to force of friction over the mass. And then this should be equal to 0. Cool. Why do you keep spamming sound effects? Why not? I don't fucking care. It's my stream, dude. Anyways, okay, cool. Yeah, okay. Good, that's a good question there. What about $300? How about you pay me a Bitcoin, dude? I'll do it for a Bitcoin. You want to give me a Bitcoin? Single Bitcoin, just one. All right, this was Shahir. Cool question, Shahir. Which your question was 33. Cool. All right, I got 5 minutes. 5 minutes. Then I really do need to eat because we've been streaming for almost 5 hours at this point. Only what Bitcoin? What a steal! It's a discount, man. 1 Bitcoin, I could quit my job and just do this for you guys for the whole year. It'd be great. All right, let me see all the other fun questions that got added here today. Scan. This is a cool one, actually. Here, let's do this. I like this. Let's do this one, dude. Yeah, Scan, I got you, bro. Okay. In the setup shown above, a student uses a motion detector to determine the speed of the cart VI before it collides and sticks the stationary cart with mass M. Motion 2 detector speeds VF after the collision. The student repeats the experiment several times. Here you go. This is how you improve the accuracy of your results. The slope on this graph is most equal. Okay, interesting. So they do a graph of graph of VF as a function of VI. Okay, that's very cool, actually. Let's see how this works. So here, they're going to do VF versus VI. Okay, VF versus VI is that. Mathematician, you're in my Discord, dude. Just send me a DM, dude. You're fine. Okay, let's think about the speeds. Okay, so initially, only this one is moving. So you're going to have that P is equal to little m VI plus big M times 0, right? That's the total momentum in the beginning is only this one is moving. And then after the collision, and then we say it sticks. This is the important thing. Also, what type of collision is it if it sticks? Is that elastic or inelastic? That's another question they ask. Okay, final, you have P is equal to little m plus big M, all times a single velocity, which is VF. Okay. Yeah, I know the graph questions are weird. So always write what the axes are, and then use the equations to try to get something that relates the two of them. So, perfectly inelastic. Yes, exactly. Thank you, King, for all the help. I'm still cooked, but I feel better. Yeah, good. I mean, good luck, demo, dude. Good luck. Anyone here, because you're here, you're already learning some stuff. Again, it's better than just doom scrolling and not learning shit. So, like, pat yourself on the back. Good job. You guys are doing good. Okay. So, these have to be equal to each other by conservation of P, conservation of momentum. So, I can say that MVI must be equal to M plus big M VF. And then let's remember what we're trying to graph, right? I'm trying to graph VF versus VI. This is usually Y, and this is usually X. And let's remember how this works. You usually have Y is equal to, like, some slope times X, right? This is how a line works. Right? Y equals MX. Sometimes there's a y-intercept, but we don't need that. Okay. So I want to have VF over here, and I want to have VI on the right. So let's move things around. I'm going to say VF is equal to MVI divided by little m plus big M. Okay. Do you see that? I swapped the order of these so that I had big M plus little m VF is equal to little m VI. And then I just took this and I divided it over to get me here. And now I have this is my slope. Because I have Y is equal to slope times X. Okay? And so the slope is little m over little m plus big M. So I think it's answer choice B. I'm going to go with B. Yeah? B? There we go. Nice. Good. Yeah. That's always the way to do it. When they say, like, this as a function of this, it's always y versus x. That's what it is. So put that on your graph, and then know that you need to get this is equal to some shit times this. And then just rearrange it so that the equations you came up with in physics look like that. Yeah. Cool. Nice. Okay, cool. We'll download that for you, Scan. That was a good one. Scansters. Which one was that of yours that I did? Sorry, which one? Scan. Oh, man. Da, da, da. Oh, it's question 32. Post. Nice. Okay, Scan. I'm going to put your question here in the Discord. So there you go. Again, all the screenshots of everything we've done, if you want to study and go look through it, they're on the Discord here under homework help. And then we have links and timestamps. You ready about to get first? Yes. In the elastic kinetic energy are conserved, correct. And inelastic, only momentum is conserved, correct. Those are both correct things, the mathematician. See, you don't have to pay me $300 for that. Okay, cool. All right, I think we're out of time. So, I'm going to end the stream. Okay. Thank you again for coming to Actual Education Office Hours. Appreciate all you guys came by. Big, huge thank you to our subscribers on Twitch, all of our Discord server boosters. You guys are great. I hope you guys found this useful. You guys are going to do great. You're going to do awesome on the AP Physics 1 exam. Thank you. Good luck, everyone, for tomorrow. Yes, you're more than welcome. Again, if you want to keep getting help, I know a lot of you guys are saying, "Oh man, fuck! I wish I'd seen this before." We've been doing this for like 5 years, and we stream 4 to 5 times a week, along with a lot of other friends. So the website actualofficehours.com, where you guys were submitting questions, there's also a link there to our streaming schedule. So go check that out. If you need help in any of your other classes, we have this. It's the same format as this. There's a lot less people, so you have a lot greater chance of your question getting answered. Today they spammed my link out to a bunch of high school teachers and stuff, so that's why everyone got the notice about this. But usually it's not this crazy, so you don't have to wait as long to get help. But whatever you're doing, math or science, I don't care. I teach chem, I teach calc, I teach stats, I teach bio, I teach all the physicses and whatever. If it's there, I can do it. So yeah, you're all gonna get 5. Good luck. I might do a stream after they release the exam to just kind of run through the FRQs. So make sure you're subscribed to this channel and you'll get the notification for it. Again, our YouTube link is here. Also, go check us out on Twitch. That's like usually the nicer way we stream. And then if you want to keep learning with us and having fun, join our Discord. We do all sorts of fun activities. We play video games. We give out gift cards for prizes. All sorts of fun stuff. So, yeah. I'm so glad. So glad you guys did as well. Okay. Good luck on your exam. We will see you tomorrow if you're around. Otherwise, best of luck. Peace.